We're live.
Ooh. Hello. Well, not yet on my screen at least.
Yeah, yes, your screen share seems to be sharing only 1/4 of
One
half.
what?
It's working now. It's fine.
Okay.
Yeah, if you go to the other screen, your sharing doesn't work.
Okay, now it seems to be working.
Yeah.
Let me hit it. Yeah, there's like a short delay. That's nice. 1, 2, 3. Yeah, it's pretty good. I'm muting YouTube. Okay, this seems broken.
Yeah, we cannot see your whole screen, I think.
Let's wait 10 seconds. Now it works. Okay, if I switched tabs,
yeah,
this is so sad. Don't switch tabs. Okay. Yeah. Okay. Should we wait for someone, or I guess we can start now?
I think we can start.
Okay. So welcome everyone to this second edition of the image matching local features and beyond workshop that is co-located with CVPR. Oh, I could not move slides. Now I can. I would like to take 1 minute to introduce my colleagues who made this organization of the workshop possible. So Vassileios Balntas, who was at Scape, and I guess now is at Facebook since Facebook acquired Scape. Professor Vincent Lepetit, who was at the University of Bordeaux, but now I think he's in Paris already. Jiří Matas and Dmytro Mishkin from CTU in Prague. Johannes Schemberg at Microsoft. This is me speaking. I'm Eduard. I'm at Google now, and my colleague Kwang, who's at the University of Victoria. Also, thank our sponsor, which made it possible to have some prizes for the challenge, which is Google. This is the, I think some is broken. No, it's fine. This is the schedule. So there is a short welcome session that is taking place now. After that, we'll have 2 invited talks that should last about 45 minutes each from Krystian Mikolajczyk at the Imperial College in London, and by Dieter Fox from the University of Washington. After, we have 2 short presentations for the 2 posters that we accepted for the workshop, which cannot be posters because we don't have a physical edition of it. So we asked them to give a short talk, which I think would be much nicer. Then we have 2 talks, which should take about 45 minutes, where we introduce this benchmark that we have developing, which is the basis for the challenge that is co-located with the workshop, and a paper that we recently published on it. Then we have 9 different talks, short ones, from different participants in the challenge, and a short closing ceremony at the end. This is going to happen live on YouTube, obviously. If you are listening to this, that's probably how you are doing this. Please ask questions on chat, and the idea is that we will try to pass them on to the speakers. It's probably a bit cleaner that way. I just added the warning in case we got a longer delay on the stream, but it seems that it's pretty good. Still, if you have questions, please just dump them on chat as soon as you think of them, so that we have a little bit of time to curate them if we get, hopefully, questions. And we encourage the presenters to have a look at the YouTube chat after they are done, because there might be some things that we cannot address, and they might want to do that directly on chat. There is a Zoom link that is available if YouTube is not working for you. That's on the CVPR, the internal website on CVPR. We didn't want to advertise it very much because some people were being Zoom bombed, as they say. But if you have colleagues who, let's say, are in China who have issues accessing YouTube, please direct them to the Zoom link. That should work. The CVPR internal website is pretty bare bones, but the 2 papers that we accepted took the steps, went through the trouble to make some short videos. So if you want, you can take a look at them if you are unable to attend the presentations. And originally, we planned for the second session that would happen 12 hours after this one. But at this point, I think it doesn't make a lot of sense. So the live stream is up on YouTube, and you can check it at your convenience asynchronously whenever you want. Obviously, trying to coordinate, I think we have 13, 15 speakers, it would be a mess. Okay, so what is the workshop about? The focal point is image matching, kind of in the wild. What do we mean by this? We want to focus on matching rigid scenes across mostly white baselines, but also differences in time, in weather, think also day versus night, that kind of thing. This has many applications, obviously, in mapping, in relocalization, in SLAM, in augmented reality, virtual reality, mixed reality, in robotics. But we focus not on these applications themselves, but on the underlying technologies that are common to all of these problems. And this basically means to this day, local features, right? That is what we have been using for many years now. But we call the workshop local features and beyond because we want to keep an eye open to see how the field evolves. We might not be doing things the same way 10 years from now. Maybe we still do them this way because we have been doing it this way for 20 years now. And we want to focus on what works in practice, right? And that is why we organize an open challenge that is focused on local features and robust estimators, such as different ransack variants. And this is a big part of the workshop. You would think that this problem is kind of solved, right? It's just matching to views of a given object, a rigid object. But in real life, in practice, it's still pretty hard to do this consistently. And that is because once you move to the real world, you have problems such as extremely large baselines, such as the one on the top layer of the image. It's easy for us to recognize that these are views of the same object. But if you want to find the exact pose, the difference in pose between one view and the other, that is very hard to do. You also have occlusions. You have changes in the environment, such as the example on the bottom left figure. You have different illumination. You have different vegetation. And also, this is quite easy to do for a small environment that is kind of controlled. But if you want to do this at a world scale, that is pretty hard. We opened the CVPR workshop last year with this slide, in which we called what we do kind of a last bastion in computer vision, where we are this poor guy on the island, and we are surrounded by deep learning, deep learning, deep learning, and more deep learning, because that's kind of where the field is at the moment, right? It's one of the last problems, I would think, in computer vision, where you still need, you don't have a simple end-to-end solution, a deep network that you can throw images at and get poses from. So where are we now? We're almost there. It's getting closer, but still not there yet. Still not there yet. What do I mean by this? So we use machine learning a lot, but still not end-to-end. We still don't have end-to-end solutions that solve this problem perfectly. You will see this when we start talking about the challenge, and you will see that most of the top submissions are still using learned patch descriptors, such as HardNet or ContextDesc on SIP key points. You will see that most of the top challenge submissions, even the ones that have learned matchers, still throw ransack on top of it, not ransack, but some state-of-the-art methods such as digensec on top of that to kind of refine the final estimates. And we still don't have any submissions that use direct pose regression, by which I mean just, you get the images and you produce a pose. So admittedly, this is because we don't give that option yet. We've been saying that we'll do that for a year. It should be relatively easy to do. But at the same time, very few people ask for this. So this is not the holy grail that you might think was the case, let's say, 4 or 5 years ago. I want to take a minute to highlight the differences between this year and last year. So one big thing that we did early this year was that we open sourced the benchmark that we use for the challenge. The code is out. You have the GitHub link on the slide. Contributions, patches are welcome. This is the basis of the challenge, and it's still pretty heavy on compute. So we spent about 100 core years of compute on Compute Canada, which is a supercomputer or a cluster of supercomputers that we use for this purpose. We also released a version of this that can run on virtual machines on Google Cloud Compute. That's pretty easy to use. So if you have issues running this on your desktop, which can be done, but runs on a single thread basically, and is very slow. You can give this a shot. And one change, a small change, but important that we did is that we made all images upright. Last year, we had some images that were flipped, let's say 90 degrees. And we think that it's a pretty safe assumption that you can move these images upright, and this makes it a bit easier for many methods that are learned to work on them well enough. We also released a paper. We have the link here, but if you cannot click on the link, you have the title of the paper, which is image matching across white baselines from paper to practice. We spent a lot of time on this, and what we wanted to do was, in addition to developing this benchmark, to find the correct methodology to tune all of the baseline methods and to do a very thorough evaluation with many methods. So there's a lot of tables, there's a lot of numbers, but if you work on this problem, you might find this interesting. There are many lessons that can be learned from this paper. You would think that many of them are really obvious, but they are kind of neglected sometimes. And you'll hear more about this on Dmytro's talk in a bit. We organized a new, improved version of the challenge. We have a link with many different visualizations. We'll also talk about this a bit later. And we made the challenge become a stronger focus in the workshop. So last year we had a couple embedded talks, which unfortunately did not happen because the building that we were doing this at ran out of power. But this year we have 9, and hopefully we don't have any issues this time around. This is the schedule. And again, I think we can just jump to the talk by Krystian. I think Vassileios wanted to do the introduction.
Yes, thanks, Eduard. So the first talk is from Krystian Mikolajczyk. No, is it better than the L, I guess, if I remember it correctly, who is a professor reader at the Imperial College of London. So he did his PhD in Grenoble, and then became a lecturer at the University of Surrey. He also won the Longet Hidden Prize in 2014 for, I think, a 2004 CVPR paper. And I guess he's going to give an overview of related methods he worked on local features. So thanks, Krystian, for joining.
Okay. Thank you very much. I'm trying to share the screen right now and put it on. Hopefully it will come up. Okay. Great. All right, so thanks again. Thank you for inviting me to give this talk. I watched your tutorial on Monday, and I have to say, yeah, it was really great. And I encourage everyone to have a look because it puts you up to date with all the recent developments. And, you know, also shows actually that those classical pipelines are still in play. And this is sort of that inspired a bit this talk. And I have to explain the title as well, which is, you know, everything has already been done, but it's really our job to do it one better. So what I mean is really when you are in the field for many years, many decades, you notice that we are doing actually quite the same thing. So Eduard said 20 years, but I would say more like 40 years we are doing kind of same techniques. And you see something new and you immediately start thinking, I've seen it before somewhere. You dig deeper and you find a paper, you know, like 10, 15 years ago, which had this idea. And quite often, actually, it may happen that it was your own paper. You just forgot about it. So that happens to me quite often. And I thought that I will look back and see, you know, what inspirations can be taken from those old methods, even though we are surrounded by deep learning, but I think there's a lot of ideas that can be brought to this new era. So this is, by the way, the background. This is the place where we would have been right now in Seattle. So all right, so let me kick off. We still use a lot of local features in the classical pipeline for basically depth estimation, for accurate camera pose estimation, right? And if we have those features, we can match them. That's really a lot of job done for the rest, okay? And then we can have a nice cloud of points, 3D model, depth, camera pose, and then do all sorts of very fun applications from navigation, SLAM, and AR, and all sorts of things. All right, so let me have a look at state-of-the-art on keypoint detectors, and show you some milestones and some inspirations, and then similar for keypoint descriptor. So if we look at this timeline scale, from 70s, when I can look actually back to the papers, like 78, people were using handcrafted features, and a lot of successful developments back then that actually survived even until now, and they are still giving extremely good performance. So then the big milestone was in 99 with 2000 with those scale invariant, fine invariant features, and that generated a lot of attention. A lot of other fields actually could progress because of that. We had MSER that is still top in terms of accuracy. And 2012 came the deep learning methods with ImageNet results, and the field shifted. It took a bit actually for features to get there. And 2015-16, first methods show that the performance can be boosted a lot. So these are the detectors, but still, if we compare to the descriptors, there is much less actually activity in terms of the detectors, and those classical detectors still perform very well compared to the new methods. So let me first review some properties that we are looking for in those features, and then how we actually try to get those working. So typically we want them to be distinguishable, to exist at different scales, to have strong gradients, right? Because then they are actually existing at different scales. So strong gradient is a prerequisite here. A robust to occlusion, so that must be local then, because part of the image can be occluded, then it will survive. Discriminative neighborhood, so again, it means signal changes, variations, and that again means strong gradient. And then accurate locations, so you can localize well if again there are signal changes in the image, so that suggests again strong gradient. So all those are basically giving tips what to use to get those features working. So in the past methods, the classical methods, typically gradients were detected with Gaussian filters. So we had a bank of filters, and we convolve with the image, very much like now the trained, learned filters. And this is how Hessian detector works. Second moment, the second order matrix, Hessian matrix of derivatives. And then we have a attention map or feature map from which we detect locations. Harris, first order derivatives, second moment matrix, again, feature map, we detect locations. Difference of Gaussian, again, second order derivatives, Laplacian, and then we detect. So all those are really, really still working very well. And this is thanks to the filters, the operators that they use, and also the combinations that are just simple mathematical formulas. So what did we do to get this good part actually working and combine with deep learning to improve the detectors? So we actually took those well-performing filters, first, second order. If we know they are working well, then there is no point really learning them. It's less parameters for the network to learn. But obviously there is benefit from learning, so we need also the learned filter. So this was the first idea. And Axel worked on this very well and designed the pipeline where we included all those good things like multi-scale, and then incorporated hard-coded handcrafted features like those first, second order derivatives on these multiple scales. Then we added learned filters, combined them all together. Again, a few learned filters and the feature map where we detect the points. Okay, so architecture is quite simple. And the question is now how to train it, and because learning is obviously the key here. So we use Siamese setup where we process images in parallel, which can be basically synthetically generated homographies or projections of images, process with Keypoint.net pipeline, generate the feature maps, and then use the loss function that is comparing the locations of features. So using some sort of soft argument max. for minimizing the error. Okay, and we do it at multiple scales. We detect features at a small window, larger window, and very large window, and those that survive over the scales, right, are very robust features. So this actually worked quite well, and we got really good results. You can see some, I think, on today's benchmark. One interesting point is that we also sort of look, when we develop, at the complexity and speed. So complexity is sort of considered a bit differently these days. So in the terms of number of parameters, and if we compare some state-of-the-art methods like SuperPoint, ASLFeat, okay, we are well with 5.8K parameters, and we also have that is simplified. We call it tiny Keypoint net, which has only 260 parameters. Okay, so that's basically speed, and that also gives you the possibility of running something on very limited embedded devices like mobile phones and so on. So when we look at the repeatability, because that's how those methods are optimized, and a number of classical methods are still there. If you see from the top, the deep learning methods are here from lift down, all right, including SuperPoint, ASLFeat, and so on. So looking at the viewpoint repeatability, so this is scale and location. So if we consider overlap error, okay, is doing very well. Obviously, if we discard the scale and we just look how well they are localized, then we get many more correct matches, and performance is really good. So you see that there is quite a lot of gain compared to those other competing methods in terms of accuracy, in terms of overlap and scale, and so on. So we have, I invite you to look in the paper, a lot of results looking at viewpoint illumination, and combined also the errors that are produced, range of scales that are covered, and so on. So overall, quite positive results. So this is one example of inspiration from the past with hard-coded filters. We also were thinking actually about how to develop good representation for detecting key points, and whether we tried, and somehow with the descriptors it worked well, but not so much with the detectors. So again, I know those papers from old days, and one of those was called an affine salient region detector, which was quite popular actually back 2003-04, and used in recognition mainly, where the idea was to find features which have high entropy of a representation within a small patch. So they used histogram of gray values, and they looked how the gray values are distributed, and then if the entropy was high compared to the neighbors, then actually that was potential salient feature. So we adopted this idea and looked at the methods that were the classical ones, which are detect, describe. So this is still sort of doing very well, as you can see from the tutorial, but also from the benchmark today. Then we have the joint methods, which do detect and describe at the same time, training, all right? And we thought, why not actually to do a method that does describe and then detect? So we call it D2D because we consider that we can have the dense representation, and we can actually start looking for features within this dense representation. There were some other methods that also exploit this idea of training the descriptors and then looking at the feature maps to detect salient locations. But our method differs because we don't do any training, okay? We are looking for high absolute and relative saliency in existing descriptors. So high saliency, all right, can be like high variation across feature channels. So we call it absolute saliency. It's just variance. And relative saliency, we are looking across spatial neighbors if the features are discriminative as well. And then this pipeline is very simple. If we take any network, any good descriptor, and generate dense features, we can then look within the feature maps, first across the channels if there is high variance, and then across spatial locations if there is also this saliency. And based on that, whatever descriptor we have, we can detect features that are actually good for this particular descriptor rather than for some other measures. So that actually allowed to test the method with many other descriptors, because that can be plugged to anything. And we could see some nice improvements. Those dashed lines are actually the combined detector with things like HardNet or SOSNet. And here, when we compare with methods like D2Net, for example, or SIFT plus HardNet, SIFT gives many more features. Our method gives actually less features when it's combined with HardNet here, but more matches. So these are the matches, and these are the total features. So this is quite positive effect, lower complexity and better results. Okay, so that was our second idea that came from some past methods. Now let me switch to descriptors and talk a little bit about the patches and how we progress there. So I have similar sort of timeline here, and normalized cross correlation has been used since 60s. This is actually computers were used, or since computer vision was being researched. And it's still a quite good metric, but it's obviously taking directly the image, so it's not very convenient because of dimensionality, and there might be better ways of making it more robust, more compact. So things like local jets, steerable filters, and moments were in the 90s very popular. So these are either image derivatives, first, second, third order, they're combinations which make features invariant, and so on. Some statistics, all right? So local binary patterns were actually for a long time really state-of-the-art for texture descriptors, and then used for face recognition for different applications, and also for matching patches. SIFT, so that's a big milestone in the development. From that, there were a lot of methods that paid attention to invariance, affine, scale, and also efficiency, because SIFT really demonstrated that things can be efficient run on the laptop. We had then in 2008 first methods starting to learn better descriptor. This was also due to the occurrence of the data sets for learning and better running of images and learning. So that showed the potential. But then actually the efficiency came into focus a lot, and we had quite a lot of years of binary features being very, very popular and very fast. So that was, unfortunately, actually, we don't see that much now, because they are far behind in terms of performance, and it's not straightforward to do this on also on GPUs. So also some extreme cases where and across modal matching were in focus, and then from 2012 a lot of methods basically using on CNN applications. So I'll have a look later on timescale of CNNs in particular, but I want to give a few examples of descriptors that we worked on, especially the binary ones. So the binary descriptors, as I said, were quite popular. I started with brief, where very simple random tests were used. That also the idea came a little bit from decision trees and classification using decision trees, where simple tests were popular. So here the idea is to take 2 pixels, compare, and if one pixel is greater than the other, then it's 1, otherwise it's 0. So we have a binary string, and that string can be a descriptor, and it's obviously extremely fast because we can sample just directly and compare. And then also the direct hardware commands in CPUs allow to run Hamming distance extremely fast. So that was really, really popular and working well. And there were a lot of variants those features. So we actually were thinking back then that this, because it's very fast, so it's very suitable for any online problem matching, like in videos, but also for maybe online learning. So our first attempt was really to look at the videos and whether we can improve matching by using the data, using temporal consistency, using positive and negative examples. So given starting from a single positive example indicated by the user and using this set of tests, simple set, random tests, okay, we could start matching from first to the second image, and at the same time we could have a positive and negative examples, samples from different places in the image, and we could start a little database for actually learning better and better descriptor. So here's the pipeline. All right, so the data is basically unlabeled apart from this one single example, and we use a simple classification technique and then collect positive and negative, we call them experts. These are really examples. So here are positive on the left, negatives on the right, collected in the video, then goes through some testing set and back into training and improving the classifier. So that was working surprisingly well, and actually surprisingly fast as well, and could adapt nicely to the patterns. So what we then noticed is that these binary tests actually can be different, can lead to different results if we just use different set of tests. So even the same method and starting with different seed, it could somehow for a specific object, you know, have a better set of pixels, and the results were quite significantly different, even up to 10% going up. So we're thinking how to make use of this, right, and try to adapt somehow on fly to the image, underlying image. So that led to the idea of binary online learned descriptor, where now we actually worked with static images, but we wanted to adapt features during matching. So if we have a query patch A and B and we want to compare them, we can, you know, with the traditional method, we would just take a fixed set of tests and apply to both and then compare the string. But this set of tests may be suboptimal for some images. So the idea here was, if we have more examples, we can test these binary comparisons and choose the ones that are better, more stable. All right, because if we take a test that is within the flat area, then obviously also it will be unstable due to noise. So that resulted in different tests for different patches. And the question was now how to compare those. So we came up with the metric that actually is using at the same time the binary string describing the patches, but also using the mask that says which locations are used for testing. So that increases the dimensionality, but then the gain actually in terms of performance was quite significant. So the results and comparing between the learned features, right? And the learned features are from single patch that is then transformed with synthetic examples, just simple, you know, homography projections. And compared to the global one, we can gain quite a few % of performance. And this is on old UBC data, because back then this was probably the only one that was suitable for any learning. So if we compare to other of the art methods that were back then, this bold descriptor was doing quite well. There was one called Bean Boost that was much more optimized and wasn't real time and was actually not working on binary tests, but it was binarized real descriptor, so it was performing better. But in terms of speed, we were doing quite well. Okay, so that, you know, brings us 2015 to the time when deep learning methods started to perform very well in terms of descriptors. So we could see the optimization actually gave massive boost in terms of error. Obviously, the efficiency was completely abandoned, but the gains, in terms of matching accuracy were massive. So the development, all right, from 2015 was quite quick. There were a lot of this is not full list. There are many more, but some more important ones include from 2015, like the compare the desk MatchNet. Okay, and then also Lift that attempted to do first full end-to-end pipeline for detector descriptor. And then those that you're more familiar with, things like HardNet, L2Net, and so on. So I did have a look at those descriptors, and many of them we can see actually are building on the same architecture or the same backbone, that is L2Net. Quite a lot of them, and still until now, actually, quite a lot of them is using the architecture, which was very well designed, of L2Net. And the main focus here actually is quite often just by introducing different loss function or different way of training the method. So this, I think, over the past couple of years, it's not negative. It's actually just an observation that it was something that did bring improvements. Just the training process. So what was particularly successful over this past few years is the way of training or the way of using the examples, and especially the loss based on triplet loss. Okay, so everyone is familiar, whoever does any matching, with triplet loss. And if we look back, actually, the triplet loss can be traced maybe even earlier, but I found some material actually a couple of decades ago. So we have for distance metric learning a number of methods that were exploiting this. So back then, distance metric learning was using matrices, projections, nonlinear projections. So we had features, and then we had an optimization process, and the whole idea was to come up with a matrix, with the projection matrix that in the form of Mahalanobis distance, right, would project features to some better space for comparison. So one of the ways of optimizing was to use a triplet of features, and to use this formulation where we have the distance between positive, the distance between negatives, and margin. Okay, so very much what we have in standard triplet loss. And back then, the things were actually formalized in terms of for objective function for minimizing, and subject to some constraints. So the objective function was either based on this matrix or some distance between features, and then constraints that the features had to satisfy, right? And that was then with quadratic programming that was then trained on some data where actually all the data was used at once. So it's not like iterative process now with backpropagation. So we had similar features in the set D, right? That were basically dissimilar pairs, and S were similar pairs as the objective for minimization. And we had some of those to optimize, and then constraints, also some of constraints together. We could, in addition, have some slack variables there in case this solution cannot be found, cannot be exactly satisfied. So this, we're looking back to NIPS paper in 2002. And then even closer to this, also in NIPS 2002, for distance metric learning, where we have directly these positive, negative distance examples within the same distance larger than 1, and the objective function is the norm of A matrix, where A is basically the projection, nonlinear projection of features. Okay, so this triplet then had obviously a lot of success in matching and also other areas. And we were also looking how we can use it in our methods. So one first example that we had is back when those methods started. So a standard triplet is picking two pairs, anchor with positive and the same anchor with negative, and then using the optimal softmax ratio for the loss. All right. What we noticed back then is that if we use different anchor, that means if within the triplet we look at the anchor, because we have two positives, so one of the anchors may be actually closer to the negative. So we can see it like some sort of a soft or a very tiny hard negative mining within the triplet. And we could pick the tougher one and then use that in the optimization process. So that was work that Vassileios was doing back then. And we also were concerned about efficiency in all our methods. So we used very simple shallow network, okay, few layers, and then trained, okay, on the UBC data and tested. So in terms of efficiency and dimensionality, so that's dimensionality and time for extracting features, computing descriptors. We want to be somewhere lower in the corner, all right? So then that gives us efficiency. And for comparison, things like deep compare, MatchNet were really sort of far here at the beginning. So when we compare to standard SIFT on CPU, all right, or brief, we see already the difference in performance. And with this PNNet or TFeat that we call it now, we were actually not too far behind. Okay, so this great, and then the results obviously in terms of performance were also important. So when comparing on the UBC data, we were comparing against standard hinge loss using, and then the gain was quite significant in terms of loss and training. So this is a false positive rate error that we used for this data set. And also when compared to a softmax ratio triplet, that we observed also by this anchor swap quite nice improvement. So for comparison with other methods back then, we looked at dimensionality and we looked at standard error. All right, so we're going from SIFT with 128 dimensions, a level of 27, 29, so average 26 error, false positive rate at 95. You see the first sort of convex optimization, which is not deep learning method, still brings massive improvement, and then deep learning methods go down, 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 and with the proposed triplet, we could even get down to 7. So with methods that we have right now, we are far more or lower in terms of error that I will show you on the next slides. Okay, so another interesting idea that we had some years ago with the classical methods and with the new deep learning methods is based on second order statistics. So bags of words, okay, were for those that started within the deep learning times, probably heard about it, but that was like now deep learning. That was back then like deep learning is now, and we were optimizing as much as possible bags of words representation. So the idea was to have local features, descriptors, collected from the image, code books. So basically exemplars against which we match. So these are the descriptors come from the image. We match against code book and we have their representation. So basically some way of representing similarities between our code book and features in vector form. And what we thought is that this is first order okay, occurrence. And then we use different ways of pooling also those methods, but that was not within deep learning, but was sort of classical handcrafted. Then we had the idea that higher order can be also exploited in this context. So if we take those vectors of packs of features and we just use tensors of different orders, so like products with themselves, and generate feature maps from that, that may improve the performance. So here is basically we take the product, okay, between the two feature vectors, and we obtained a second order representation. So that's exploiting higher order statistics, and you could even go higher with this, but obviously noise then starts to play a lot of problems. But up to second order, the improvement was quite significant, and state-of-the-art method like spatial pyramid matching, like feature vectors or VLAT, okay, they were all sort of improved by using this second order statistics on different data sets, quite consistent results. So when we compared to state of the art, right, the results were really good. So now 3% improvement is always fantastic. Sometimes even 10 on different data sets. So this was quite significant. But already back then we had some first results classification on CNNs, and if we compared against them, then it didn't look that good. All right, they didn't exploit much, second order, just a simple sort of learning of features, and then the improvement is massive. 10%. It almost many data sets. So that obviously didn't inspire any confidence into continuing with bags of words. But the idea of using higher order statistics is sort of we're still not bad. So we were thinking how to use it in the new setup of deep learning, and again within a good training by triplet. Okay, where we have positive and negative pairs, so anchors and positive, and first order loss is basically standard triplet loss. Then there was a paper SOSNet that proposed to use also second order statistics from the distributions of distances. So now we are looking at how the distances between anchors and positives are distributed, and how the distances between anchors and negatives are distributed, and if those distributions are sort of far, then this is what we want. So this was a second term that was added to the first order loss, and that showed quite significant improvement. So that was state of the art last year in terms of matching. So we proposed something related based on that, but also added the idea of self-attention, so second order attention map into features. So Tony was working on that, and looked up on recent methods that use a lot of transformers or second order, basically attention, self-attention maps that were quite successful in many other tasks. So we then designed a block, a self-attention block, where we can basically plug it as a layer in between any two layers of the network, or within the layers of the network. So that's basically a method of reweighting feature maps to focus attention on more useful features. And we can use any sort of CNN backbone for reweighting, and then using standard generalized mean pooling to calculate descriptor and test it. So training was done in a very similar way with the triplet. So we have a Siamese setup, then positive, negative examples, and first order and second order loss training of those attention maps. Okay, now we run several tests and on different data sets. So for here, I show just the results on H patches, but we also have results on the retrieval that are quite promising. So where we compare with previous version, that is SOSNet from last year, state of the art, and so that outperforms HardNet. And depending, you know, how many of those layers we plug into the network architecture, right, we can get different improvements. And the best is when we have in third, fourth, and fifth layers. And we have the results for patch verification, matching, and retrieval. And on H patches, the improvement is consistent. So what you have to compare is against SOSNet here, okay, up to here, the Solar descriptor. So this is how second order statistics we try to exploit, and got some success with this. But given the good experience with hard-coded filters and object key point detector, right, we wanted to incorporate naturally into the descriptor. And here is our attempt to that. So now we looked at things like SIFT and Gabor filters that were very often used for matching and sort of resemble a lot the filters that are trained. So traditional pipelines were using banks of Gabor filters convolving with the image, and then using responses of those maps, also some sort of quantization and pooling, histogramming, okay, and compressing the feature because there were a lot of filters. So you have an example of frequencies, different orientations convolved with the image, these types of feature maps. So we're not learned, all hard-coded. Okay, so the idea is very similar to what we did in Keypoint.net. So we decided let's use those good features and add to standard pipeline like L2Net, where we can have extra learned features, but the Gabor and derivatives will be there at the beginning. The same with multi-scale image, all right, to gain some robustness against changes. And the features are fused, and then we have the descriptor map at the end with dimensionality, dense, basically descriptor dimensionality 255. So the features are basically rotational convolutions. So we have input filter, and then we use rotational convolution for generating rotated feature maps, right? We also break it down into positive, negative feature maps, right? And use cyclic pooling, basically because filters with orientation are cyclic, right, after 360 degrees. So this is the hard-coded features, right, followed by L2Net and feature fusion. So now how do we train this? So we try to train the detector and descriptor at the same time. This is still quite difficult. That what we see in many methods is that, you know, these pipelines are not exactly integrated. So we here have an approach that alternates, but still uses the descriptor to train the detector. So we use the Keypoint.net architecture here, and the descriptor that I just discussed. And we use the loss functions for the descriptor and the detector, but also use the triplet loss and gradient from the triplet loss on the descriptor. Okay, so we can pick positives and negatives from feature maps and backpropagate through the detector to improve also the repeatability, the detection scores. So this, then when we look how much different components contribute, right? If we start with L2Net backbone, so we have, and fully learned features, we are on the level of like 42%, and start adding first order derivatives, second order hard-coded, and then Gabor filters hard-coded, right? And then those positive negative maps and also multi-scale, we arrive on nearly 3% improvement from this pipeline. So there is basically a positive message that sometimes things don't have to be learned and can be incorporated directly if they are good, if they prove to be good in past. All right, so with the triplet, as you see, has been used quite extensively over time. And now our last attempt to that was to look more closely what happens there with different metrics. So we have the triplet loss, and there is the similarity between positive pair and negative pair. And we can have this theta angle because we can show that if we use things like correlation, like inner product, for similarity between features and then normalized inner product, then it's down to the angle between vectors, between feature vectors, right? If they are normalized, it's just how the angle differs. So all depends then similarity on the angle between the descriptor vectors. And the same is for the L2 norm features. If we normalize them, it's slightly different, but it's also fully dependent on just the angle between the features. So if we look now at the distribution of positive and negative pairs, then it's within the half pi, okay, range where we have the positive and negative, and then for different descriptors is very similar. So this is basically down to the metric rather than to the actual network architecture or whatever filters we use. So we started to look how those metrics differ and how gradients from those similarities affect updating the descriptors. So the gradient from that inner product, okay, straightforward to calculate, we have this. And then the gradient from the L2, we have that. And now if we plot that, right, we see that the the gradient from the inner product, all right, is this sign here. So what it means is that it has very small gradient magnitude if the similarity is low. Okay, the problem here is that if the similarity is calculated between positives and it's very sort of low, then it's okay. But if there are negatives, okay, if this is a negative examples and we get the small similarity, they also get a small update. And if we switch to L2, all right, then we have opposite situation that we have similar things by the end of the scale here, all right. And again, if we have positive examples that are actually quite dissimilar and there is a high sort of difference, then they also generate a small gradient, small update. So the idea here was that, either of those is actually not optimal for taking into account both positive, negative examples and when they should generate larger or smaller gradient for updating in backpropagation. So this comes directly from the loss, which is at the end, right? And then with chain rule, we basically propagated to all the layers before. So what we proposed, and that was Jeroen's work, is to take this into consideration that positives and negatives generate different gradients for easy and hard examples. So we proposed a combined hybrid metric, which is weighted by this alpha parameter, and then it's between inner product and L2. Then we can plug it into the triplet, right, and have this hybrid for positives, right, with the alpha parameter, which gives us the balance between the metrics and some regularization. That is also something we proposed in this paper. So what we get from that, all right, it's very interesting. Just by changing the metric and training and then following the standard protocol on UBC, we can go down now to this error, which is really small, okay, compared to SIFT and all even before the methods. So this is the data is basically almost done, saturated now, right? So on H patches, we get also nice improvement over HardNet and SOSNet, right? And on structure from motion problems, you will see the results on benchmark, because this is what we used in combination with Keypoint net. Okay, so final couple of slides on efficiency. Unfortunately, not much attention is paid to this for the matching, but right, if we look at the efficiency, it's a bit different these days. So here we have some comparison between deep methods and the classical methods on GPU and CPU, how they differ, right, in terms of speed. Now, how to improve efficiency in CNN? Well, basically, we calculated in terms of number of flops for single convolution. This is proportional to the size of each dimension. And that means basically the parameters of the network. So tensor size and number of parameters. So increasing efficiency means decreasing the number of parameters. And for mobile applications, this is critical. So what we looked at is L2Net, because that's the most popular, and see where those parameters are. So if we look at the layers where they are distributed, the final layer, these are the parameters, and this is in the first layer. So there is no point of working on all thing. It's okay, when we reduce, we have to reduce here. Okay, another thing that we can look at is how we compare to SIFT. So we have like L2Net 1,350,000 parameters. Okay, performance is obviously very different, but the number of parameters massive. So another interesting observation is not all those parameters are equally important. So we have features or kernels that are generating feature maps with high variation in the first layers, in this layer 6 or 7 in the final layers. All right, so at the beginning, and then there is a lot of filters that generate some small variations. So we propose the method actually to reduce that, and I encourage you to look how to gain like tenfold, reduction in number of parameters. Okay, so that brings me to the final slide to summarize. My observations, and I guess from the workshop organizers as well, is that we do still need benchmarks and nice evaluation protocols, right? So we can compare the methods rather than actual training data. Then recent approaches, a lot on the training, okay, on the laws and so on, which is not bad, but maybe there is something to do in the architectures as well, especially from the efficiency point of view. Descriptor development, but less detector again, so that says something. Okay, there are a few examples of integrated pipelines for specific tasks, but they don't seem to generalize that well. I mean, still, this is for practical observations. Matches are extremely important, like SuperGlue, you will see, right? That makes a massive difference for the rest of the pipeline. And again, there is little work on improving efficiency, which should be addressed as well. So with that, let me thank to all people that I work with and contributed in different ways to this work, and let me take questions if there are any.
Okay, thanks, Krystian, for the great talk. We have a few questions. Let me just read a few of them to you. So one we have from YouTube is, some papers learn features with self-supervision, synthetic transformations. Others use correspondency supervision from SFM. Do you think strong supervision is needed, or should we focus on self-supervised methods?
Obviously this is down to the data set that we have available. If we have this data, then it's better to use the real data from specific domain. This will always work better. Obviously, we know the power of nets and how they can overfeed, and if we can limit within the domain, then that's excellent. That costs, but if the annotation is there, then absolutely should be used. If for general problems, or if we don't have, then we obviously need methods that can learn from synthetically generated data, and there is a lot of work on that in tasks, computer vision tasks, where the annotation is really, it's not so easy to generate for us. Synthetic means homography, which is straightforward. 3D a bit more difficult. right? We can have still a lot of 3D now with standard reconstruction pipeline and include. It doesn't seem to always help. We don't know exactly why yet, but yeah. So there is still a lot of work to do, and I don't think any of those should be just chosen and the other abandoned. I think we should still exploit both.
Okay, thanks. So we have two questions from Harpreet. I'm going to choose the second one only. Sorry for this, but it's due to time limitations. So how do learned detectors, descriptors account for affine and other warps?
Account for?
Affine and other warps, affine transformations.
Affine transformations, the learned ones. Okay. So there are some examples, Affine-Net and spatial transformers that try to address the problem of affine. If you mean, the invariance in general, so we don't these days incorporate perfect invariance. It's better if we have some control over that. So this is why we don't do like 360 rotation for everything, because there's no point if the things don't rotate in the data. The same with affine transformations. There are not that many that go to extreme. So if we look at the traditional methods like affine, Harris, or Hessian, I think from Dmytro's work and the tutorial, you can see that these are still doing quite well as features, and in practice are actually doing quite well as detectors. So because the invariance comes from the detector, just to be sort of clear, the descriptor is just benefiting from whatever is given. So I think there is still a lot of work to do in terms of invariance. At the moment, we just do robustness that comes from the training rather than explicitly address that. I think multi-scale that we do, that's a must now, and that's also robustness. That's not really invariance, I think, in any way.
Okay, thanks. And the last question before we move on to the next talk is from Thomas Malisevitz. So what is your favorite trick from local feature design that has been essentially forgotten by the younger wave of researchers using deep learning? If you have any such trick.
Yeah. Okay, so thanks, Tomasz. That's a good question, actually. I think there is no like single trick. I think this multi-scale thing and the fact that we used to play a lot engineering things back then rather than training from the data, led to good understanding of the problems rather than throwing optimization at it. And I think the use of Gaussian, I think, and derivatives of Gaussian is what I value, maybe because this is something that I made my PhD on almost. But I still think there is great because it's also theoretically nicely funded. So I think I like those methods that have really nice foundations. So I grew up in my PhD on papers from Tony Lindeberg, where there is a lot of this affine and scale, and there is very nice analysis that you can find in his book. And that really gave a lot of inspiration to the methods that were developed in the decade later. But these days, it doesn't get mentioned even. So I think this should be looked at.
Okay, thanks again, Krystian. I think we should all thank Krystian for the nice talk. Thank you again.
Thank you very much.
Virtual clap, sorry.
Okay, let's do that.
Okay, thanks. So moving on to the next talk. So we have a talk from Dieter Fox, who's a professor in the Department of Computer Science in the University of Washington. And he's also leading a robotics research lab, I think, in NVIDIA in Seattle.
Yep.
And he has many awards, too many to say now, but one of them is the CVPR2020 Best Paper Award with Richard Newcomb, if I remember, for the dynamic fusion paper. So thanks, Dieter. We're looking forward for your talk.
Yeah, thanks a lot. Let me start sharing my screen. Here we go. And I hope that works.
Yes.
That's good.
All right, perfect. As a warning, I sometimes once in a while have like a 15 seconds dropout with my internet connection for some, I don't know, I haven't figured out why, but I hope we'll get through this. If that happens, maybe the best would be if someone just waves, because then I can see it on the right, because I can't see any chat window here. So, okay, so what I want to talk about is some work that we've done in the context of robotics applications that uses matching inside, but where the ultimate goal is actually not so much like matching per se, but it is implicitly a really core component of these techniques that we've developed here. And I'm going to look at two applications. One is for navigation, visual navigation, indoor robotics, and the other one is for object pose estimation. So again, the key purpose was not kind of the kind of assessments that I guess you guys do when you really focus on matching techniques per se, but more on the application of those. So I hope that you can see some interesting applications for your work and also give me feedback on certainly how we can improve those. Okay, let me go to kind of an overview of where I want to go. So for the navigation, for example, why would we ever want to do image matching for robot navigation? And it shouldn't come as a big surprise to many of you, where the idea is we have a robot that has explored an indoor environment equipped with a camera, and we somehow want to reuse those images kind of as a representation of the environment. Okay, and then of course the question is, how can we do this? And the matching process comes in here in two connections. One is if we would like to navigate to goal positions that are defined by images, then the robot should somehow match its current input to these target images. And also we want to use kind of prediction of match success in order to perform tasks that of course are well known in SLAM and mapping, like loop closure detection. And then in the context of manipulation, the idea is that we want to do for manipulation tasks, if you want to use 3D object models, then often it's very good if you can estimate the 6D pose of an object, XYZ, and rotation, which means like matching object models into a scene, right? In this case, you're kind of doing the matching process by changing the estimated pose of your object and then re-render and try to improve this through consecutive kind of matching actions in this case, right? And in this case, also going beyond just the pure matching, but scoring similarities, for example, can also be very important for other kind of tasks. For example, if you don't just want to use a single 6D pose estimate, but maybe a full pose distribution. I don't think I will have time to go into this, but maybe in the discussion then. So I assume I started at shortly after 9:40, so I'll count on 40 minutes from then. Yeah, okay. So first part is on where this work was motivated on learning visual navigation. For indoor robot navigation, of course, robotics community, we've been developing for decades laser-based navigation systems. And these work actually very, very well, right? Where you do standard SLAM techniques, laser scan, alignment, we can do loop closure, we can generate 2D or 3D occupancy maps and can then do path planning in them. But there's been a recent push, especially by the computer vision community, to see if we can do navigation in indoor environments, especially using visual information only. And part of the motivation here is that we want to avoid this notion of building accurate metric maps of the environment, but maybe graph-like structures or kind of representations that are, let's say, more similar to how maybe humans represent their environments, because it seems clear that for a large-scale environment, we do not have an accurate, detailed metric map of the environment. Okay, so the idea is exploring kind of alternative representations that can be used for visual navigation. There's been a lot of work on that. Often these works make some assumptions that are coming from a robotics perspective are not always super realistic. So for example, they assume that the robot always knows where it is, so there's no pose uncertainty. They also might discretize the action space into like either moving forward, turning left or turning right or something like that. And also ignore the fact that actions are stochastic, right? And these are, of course, all the kind of problems that in robotics we've been dealing with for quite a while. So when we started looking at this domain, we wanted to see if we can get a robot to navigate through indoor environments reasonably robustly using visual information, but without making any of these assumptions, which means we want to deal with continuous control. We don't want to make assumptions that the robot is told where it is. We want to be able to automatically detect loop closures when the robot kind of navigates around, and it should hopefully work in the real world, right? Which means we want to be able to train that system in simulation. In this case, we use the Gibson environment, which is a 3D, as you can see here on the right, simulated environments, but the images were taken through Matterport, so they are high quality real images that went into these 3D models. Okay, and then we wanted to see if we can even transfer that to the real world. So in this whole context, what we want to do is kind of where we say the robot observes a current image and it needs to navigate to a goal. To do so, it has some spatial memory, which is kind of the map of the environment. And I'll talk, of course, about like what that looks like. And it uses a planner and then generates control commands in order to guide the robot to the desired goal. Okay, that's what we want to build here. On the first part is kind of the low-level controller, and we actually designed kind of a two-layer controller, and I'll give you a little bit more detail, especially on the higher level. But the idea is as follows. So on the left, you can see this is a standard, let's say, laser-based navigation system. So we have an occupancy grid map. This is generated by flattening out a Gibson environment. So it's kind of the black areas are obstacles, white is free space, and gray is free space. And in such a system, as I said, using traditional robotics techniques, we can perform very robust navigation, actually, right? So, for example, if you want that robot, which is shown here on the kind of upper left, to go to a goal location, you can do path planning using value iteration or A-star style planning, where you can see this path from the goal to the robot. And then we can guide the robot to that goal using kind of laser scans that the robot uses to detect the obstacles. And you can see this green dot that is kind of guiding the robot to avoid the fact that this local controller might have local minima. So we have a global planner that is doing something like A-star, and it's kind of generating on the fly intermediate waypoints that the local controller should go to, okay? And that local controller takes care of things like obstacle avoidance and stuff like that. That's a pretty standard approach. Let me just show you this again, where especially you might want to pay attention to this green dot that is kind of, it's like a carrot stick that is kind of guiding that local controller to follow it. So what we're doing here is we're going to use that system as training data to train a vision-based controller. So again, that system is using laser scans, but we can use it to collect a large set of data in these Gibson environments where we provide the desired behavior and along with the images that we generate for the Gibson environment, right? And then we can want to train a controller that can guide a robot through these environments as well, okay? But using vision information. And the first part is a low-level controller. So, but where we want to go is we have broken this into two parts here, where again, the input to the system is a current observation and a target observation. In this case, let's assume that the target observation is actually reasonably similar to the current observation. And we'll see how we can expand on that later. And what we do is first is, wait, So first is we have a so-called high-level controller that will take a current observation and a target, and it's going to generate a waypoint relative to the robot, which are these kind of little dots that you saw on the previous animation, that will then be fed into a low-level controller. And the low-level controller takes in a waypoint and the current observation, and it's going to generate then continuous velocity and steering commands. Okay, and it turns out that rather than training a system that goes immediately from current image and target image to steering commands is by far not as robust as going through this two-layer system. Okay, and the main idea here is with this with the low-level controller. Let me put my laser. So the low-level controller, it will take care of some low-level obstacle avoidance, and also the fact that the robot that we have is kind of a car-like robot, so it's not holonomic, it cannot move in any direction. So the low-level controller also will take care of things that are due to the kinematic and dynamic constraints of that vehicle. Okay, so the idea is that the high-level controller doesn't even have to worry about that. It just tells the low-level controller where to go. Okay, so we can train the low-level controller, as I said, using this automatically generated data. And what you can see here on the left is now the behavior of that, where on the top you'll see the training expert, how it would navigate to a goal. Okay, and that is using laser scans. And on the lower part, you see the behavior of our low-level controller achieving that same goal, but using visual information only. So you can see here the robot is navigating. So again, it's a car-like robot, so it has to actually back out to do a tight turn. And you can see that it nicely circumvents that obstacle and then ultimately gets to the goal point. Importantly, the goal point here is represented through a relative waypoint, not through an image yet. Okay. What's nice about this training in the GIPS environment, that it actually works in the real world as well. So what you see on the right side is the robot navigating through one of our department buildings, where in this case, the robot is here, the goal is on the right side, and the robot should navigate there. What you should pay attention to is mostly maybe on the right side. You can see the egocentric camera image of the robot that it uses for navigation. And on the lower right, you can see kind of just a top view to show you better how the vehicle is actually navigating. Okay, so this is again a system that's solidly trained in simulation, and it works actually pretty well in the real world. Okay, and there you can see it also avoids these obstacles, even though the goal point is around that corner. So it pretty nicely actually goes around that corner and then gets to the goal. Okay, and it also works if you put like obstacles in the way of it and things like that. As a caveat, this is not quite as robust as a system that is also using laser scans as additional information. Okay, for some of the future parts I'm going to show you, we actually did use some laser scan information to that learn controller as well. So now let's go to the high-level controller, because that's more relevant to what you guys might care about, which is closely related to matching, where now the idea is, again, we have an observation and a target image, and that high-level controller should generate from these two a waypoint relative to the current vehicle position. dx dy, you could imagine this being like forward and to the left or right of the vehicle. And that will then be fed into the low-level controller that I just showed you, where the low-level controller is going to take care of kinematic constraints and stuff like that. Okay, and that network takes as input actually the multiple images. So it takes as input the current observation stacked with the target image, but in order to give it a bit more context, we're also giving it as input some images that were taken before the target location and some images that were taken after the target location. Okay, and that turns out makes it more robust. In principle, we could also just give it the target location, but then it's not quite as robust. Okay, so the input are these multiple images. We encode them, and then the important part is that we can train it again using the same data in the GIPS environment. First, to regress to an XY waypoint. Okay, So that's the relative point that's going to give into the low-level controller. We have an auxiliary loss here to make it more robust. And we also have a binary classifier that says how similar the current observation and the target is. So for example, if the robot reaches the target location where the image was taken, then that is going to return 1, which means that it might, for example, switch to another goal point or something like that, right? So this is just kind of determining how similar they are. If, for example, the robot is looking in a totally different direction, then that will return 0. Okay. So as I said, we can this that we can generate in the Gibson environments using our laser-based system, and we're just training it to replicate, to generate these intermediate waypoints. Okay, so there's no, let's say, explicit image matching criterion in there, but if you think about it, what that controller is doing is it's doing kind of image matching through robot navigation. Okay. So here's an example of how this then works. You can see here the robot again. The goal is the green dot, the thick one. The little green dots are the kind of additional waypoints that we're giving it, that we're feeding into the network. And the purple dot, that's the important part. That is the waypoint generated by our high-level controller. So that's the waypoint generated by comparing the current image and the target images. Okay. And on the right side in this animation, you'll see the current image with the waypoint projected into that image, right? And down there, you can see the target image. So you can see here that the vehicle actually, again, it's a car vehicle, so it has these kinematic constraints. Here it backs out once briefly, but then it actually nicely gets through this doorway. And then through the waypoints, it's guiding the robot to this goal point, and at the end, it actually reaches the goal point, right? Let me give you another example. Here's the current robot location, and this is an easy one where it's actually pretty clear. But if you look at the images, they are not quite like super easy to match, or there's not like a very significant overlap between them, right? But and you can also see that these generated waypoints, that initially they're not even, like, say, on the target position, and they don't have to be, because they only have to guide the robots to get there, right? So they're just these waypoints for the low-level controller. But as the robot gets closer and closer to the target, the waypoints coincide more and more with the target location. And then ultimately, as you can see, that it's more or less matched the target image with the current image. Let me give you one more example here. So here the robot is turning first, and then over time, it's going to get there. Okay, and you can see that it matched these images actually pretty well. Okay, so this is just the first step if you want to build a navigation system, right? So what we have so far is we have a controller that can go from current observation target image and can somehow get the robot there, right? If they're not too far apart. Now, what we can do with this is, of course, already, if we want, we can do trajectory following, which means if you drive your vehicle once through the environment and you just store the sequence of images, then we can use that sequence of images to guide the robot to follow these trajectories, right? That's pretty simple. It's just going to follow one target image after the other. And by sequencing these, it's going to replicate that trajectory more or less. But from a mapping perspective, there is some additional questions we would like to answer here. So one is, for example, on these reference trajectories, how dense do we need to store these waypoints, right? Or these anchor points, or these anchor images. So this is closely related, of course, in SLAM when we talk about keyframes and things like that, right? So one way of doing this is, of course, you just say, well, we'll store keyframes based on whatever, every 10th image will be stored. We could store them based on distance. But in this case, we actually wanted to store them based on the capability of the local controller. And I'll tell you how we did this, okay? And then another question is, if we have multiple traces or trajectories through an indoor environment, okay, so someone steers the vehicle multiple times through the environment, how can we combine these different traces into a globally consistent map? Which is, of course, as you know, very closely related to questions like loop closure, okay? So we solve this problem the following way, by introducing one single component to the system, okay? And that is what we call the reachability estimator. So what that does is, it says, it takes input, an observation and target image, and it's gonna determine, or it's gonna predict whether the local controller, if given this observation and target as input, whether the local controller will be able to reach the target point. Okay, so super simple idea where we say, well, we have the local controller, and now all we're going to estimate is if it's going to succeed on those, right? Which is, of course, in the image matching domain is, of course, the same question, like as if you would ask, is it even possible to match those? Okay, so we need to be able to predict that before actually doing it. Okay. So, this can be trained using exactly the same data that we used before, where the idea is we first train our controller. And once we have our controller, we can look back at the data and we can take arbitrary pairs of images, run the controller on them, and then detect whether the controller succeeds or not. And that will be the target output for our reachability estimator. Okay. So here's then an example for the quality of how well this reachability estimator works. So what we did is we sampled, let's say, more than 1 million image pairs, okay, from all these trajectories that we collected in these Gibson environments. And then what you can do is for each image pair, the reachability estimator is going to tell you a value between 0 and 1. We discretize the predicted probability into 100 bins. So for example, if it says 0.1, then it's going to go into this bin. And then we're also going to check out for all the image pairs that fall into this bin, where the reachability estimator, for example, says chance is 0.1, we can look at all the image pairs and check out at what percentage our controller is actually going to succeed. Right? So we have a predicted reachability, which comes from the reachability estimation network. And we have then the empirical success rate of our controller. And as you can see on the left graph, that these actually very nicely align, which means that our reachability estimator is actually pretty good. Okay. And on the left side, you can see this on environments on which the reachability estimator was trained. On the right side, you can see when we apply the reachability estimator on images that were collected in unseen Gibson environments, that is not quite as good, but still qualitatively actually works very well. Okay. So now let me show you how we can use this reachability estimator. Here is what you'll see is a trajectory of the robot as the robot is moving. And what we can do is we can just kind of use the reachability estimator to lay out breadcrumbs kind of along that trajectory. So the reachability estimator will decide whether we need to store a new image in, let's say, our map representation so that the controller will be able to replicate that path. Okay, so how this is done is we take the previously stored image and then the robot navigates, and the reachability estimator continuously estimates whether the robot will be able to reach that new image from the previously stored one. And if that reachability goes below a certain threshold, then we decide that we should store the new image. Okay, you'll see this in this animation now. So the vehicle is navigating, and you can see that it's storing these images actually very densely. So these blue dots is where we store the images, because it's turning and the images look very different. But if it's going straight, for example, it automatically determines that it can space out those anchor points much further away because image matching will be so much easier. Okay, so again, the interesting aspect here is that we are driving this solely through the abilities of our controller. Okay, so it's not a simple heuristic where we just say every 2 meters or something like that, but it's really driven by how well our controller works. Here's another example. So whenever the vehicle turns, of course, automatically the images are stored more densely because the vehicle needs more guidance. And if it goes down the hallway, for example, we can store them much sparser. Okay, and at some point here now the vehicle goes into the room, and you can see that actually now it starts laying them out much more densely, especially in this case, maybe because going through that doorway changes the visibility quite a bit. So, and on the lower right, you can then see these are the anchor images that we need to store for this trajectory. So now what we can do with this is the following. Let's assume we have these sequences of trajectories of images, so multiple times navigated through the map. They were collected totally independently, which means we have no idea where they are relative to each other. First, we can, as you saw in the previous slides, we can now use the reachability estimator to sparsify these trajectories. Okay. The other thing we can do is we can actually use images across these trajectories and run the reachability estimator on them to do loop closure detection. So for example, you could imagine that this now adds new connections between these trajectories, right? Because the robot might go through the same area multiple times. It should be noted that that is not perfect, and it can even cause false positives. Okay. So now what we have is a sparse topological map consisting of chained or linked together trajectories that we collected in the environment. Now, how can we use this for actual navigation and planning? Here's the idea: is we have a sparse topological map in the middle. This is the current observation on the left that the vehicle has. Okay, this is what the car sees. And let's assume we have a goal. And similar to techniques like probabilistic roadmap techniques, what we can do now is the following. We can again use the reachability estimator to connect, for example, the current observation to that graph. Okay, and we can connect it based on reachability probability. So if it succeeds, we make that connection. We can do the same thing with the goal. And now what we have is a full graph structure where we can do planning. In this case, we're just doing Dijkstra. And the idea is that the reachability probability actually serves as a cost function. So we now look for the path such that we can connect the current observation to the goal with the highest probability. So the probability is actually our cost function, which means it's not distance. It's kind of course, somehow encoded in the density of these trajectories, but it's mostly focused on probability. And then once we have that, we have our target images, and we can now have our vehicle following these. Importantly, this linking can be wrong. The reachability estimate is not perfect, especially if there is similarities in the environment. And we can do this by replanning on the fly. We tested this in the Gibson environments, and it worked in holdout Gibson environments. Actually, we have a success rate of more than 90%, very significantly higher than previous techniques that tried to do this. But the nice thing is it even works in the real world. So here's a map where you can see in color different traces that we collected through this indoor lab environment. I think it's like 7 traces. Okay, so these were then sparsified and connected through the reachability estimator. And here you can now see the navigation where the robot tries to navigate from the current location to the goal. And you can see kind of the trace that it's trying to follow here based on the map that it has. Importantly, the robot itself has no idea about any metric space here, right? It's solidly operating in this graph structure. So now you can see how it's actually managing to follow that. So in the upper left, you can see what the input images. In the middle, in the map, you can see also the, in pink, in purple, you can see the waypoint. And in red, you can see this is the anchor image that the robot is trying to achieve. Okay, and it switches to the next one whenever the overlap is high enough. Okay, a nice part is this even works in highly symmetric indoor hallway environments. So this is a much larger map. Okay, and in this case, the robot wants to go from down here to the up. So this hallway length is, I would say, I don't know, 80 meters or something like that. So it's a reasonably large environment. It turns out that the robot actually initially is mislocalized. So we don't tell it where it is even, right, as you remember. So the robot actually thinks it's more like down here relative to this anchor image. So in reality, it is up here. I hope you can see my mouse pointer. But it's choosing based on similarity that this is the one it wants to get to. And again, it doesn't even know where it is in spatial sense, right? So now you can see as it starts navigating that it keeps on trying kind of to reach this anchor images down here. But since it's at the wrong location, it doesn't really make progress in the sense of these anchor images. But at some point, actually the hallway does look significantly different when it reaches this turning point, that then it actually also is able to turn around that corner and follow the hallway. And at this point, you can imagine it is kind of localized in the map and it can successfully reach the goal point. Okay, so if you think about it, this system performs something almost like global localization and reasoning about uncertainty, but in a fully, let's say, behavior-based reactive way. Okay. As a caveat, I must say this doesn't always work. There might be some situation if the symmetries are or the aliasing is such that it really can't localize itself, that the vehicle might get stuck in a wrong location. Okay. So now I want to, in the remaining close to 10 minutes, I want to talk about object pose estimation. And this should be, yeah, also very familiar to many of those, where in robotics, in a manipulation setting, for example, if you have 3D object models in the environment and you want to kind of perform manipulation in such an environment, like you can see here with this robot, then it turns out if we have 3D models of the objects and we have 3D models of, for example, the cabinets and the doors, this is work we did at the NVIDIA lab, then you can do long-term, it's called task and motion planning, and the robot, you can control the robot to pick up the objects. What you see here in the lower left kind of display is how we track the robot and these objects using depth cameras. And this just illustrates the importance of having accurate object pose estimation and that it enables you to do full robot manipulation in these relatively complex settings. Okay. So this is just a motivation for why we care about actually 6D pose estimation so that we can use these objects. The first line of work was that we did is called that Yu Qiang did this is called post CNN, where the idea is we take as input an image and we're trying to regress to the 6D pose of an object. So this is trained on an object and using a kind of internal structure like center voting of object mask and things like that. It's trying to regress to the 6D pose. The problem with these approaches is just regressing to a 6D pose seems inherently like a very, very difficult task. So that led us to an idea, and that's being used by various teams now, of treating object pose estimation more like a matching process, where the idea is the following. Imagine we have a 3D model of an object, and this is work Yi Li did, and this was published first at ECCV, and there's an IJCV special issue coming up on that paper too, where that paper is in. So we have a 3D model of an object, we have a pose estimate for the object, and we have an observed image, and we would like to know the 6D pose of the object in the image. So one thing we can do is, with this initial pose estimate, we can render the object according to the estimate. That gives us a rendered image, and we can feed the rendered and the observed image into our network, and the network is going to predict a change in the object pose so that the rendered object model is more closely related to the one in the observed image. Okay. Now this change in object pose can be applied to our initial estimate. We get a new pose estimate. We can render that again. Hopefully it's more similar now. Feed that again into the network, and it's going to give us a new pose, and we can keep on doing this. Okay, so this is pose estimation by, if you think about matching. In the interest of time, I'm going to skip this. We had some interesting ideas on how to represent the transformation from one time step to the next, because we wanted to make it independent of scaling of the object and independent of camera parameters and things like that. I'm not going to go into this. Here's an evaluation on, for example, on the YCB object video data set, where which is a data set that has 21 objects. We can train this matching network on these 21 objects, so it has to be trained on the objects you want to match. And what you see on the right is just one example. So the data set contains 92 videos with quite some clutter between the objects, so there's quite some occlusions going on. In the lower one, you see 3D object models kind of rendered according to the pose provided by the data set. Okay, and on that data set, actually, if you compare, for example, the accuracy of pose-CNN, which was this network that just regressed to 6D pose, and if we refine that with DeepIM, this technique that I just described, then you can see that there's quite an increase in accuracy. And ADD is the difference between the, let's say, the 3D points of these objects. And ADDS is a more lenient one that just uses kind of closest point matching, and that is used for symmetric objects typically. But you can see this is a significant improvement. If we now use DeepIM, not only initialized with post-CNN, but since these are videos for tracking, we get another delta. Okay. We can also do this now with depth information, and we're getting another increase in performance, even using post-CNN followed by ICP. So DeepIM now actually outperforms even ICP on that data. Okay, and there's alternative techniques that I encourage you to look at. So the quality of these outputs is pretty similar. Post-RBPF, interestingly, is a work we did where we, instead of estimating solely a 6D pose of an object, in this context, we are actually estimating a full 6D pose distribution. And that was developed specifically for the purpose of tracking symmetric objects or objects for which you cannot resolve based on a single view the 6D pose. So there we are using actually a raw black-volaized particle filter where we sample XYZ poses of objects and then do a full 3D orientation estimation using, I think, more than 100,000 bins for all the possible orientations the object might have. Okay, if you have questions, feel free to follow up on that. I'll be happy to provide more details. I have many slides on that. And that provides, especially on this measure, like very good results, because it can handle symmetries and things like that extremely well. Let me give you one example, or some examples on, like, let's say, post-CNN versus this DeepIM. So on the left, you see the RGB input. In the middle, you see kind of a sequence of estimates that post-CNN generates on these different images. So have in mind the scene is actually static. And on the right, you see that DeepIM, the estimates provided by DeepIM, are also much more stable over time. So it kind of, I think, gives you a pretty nice idea of the accuracy improvement due to this iterative matching technique. Here's some other examples on the line mod data set where we had state-of-the-art results, where the red gives you the outline according to the initial estimate, and then the green is kind of the different refinement steps. Importantly, here is we're only showing outlines of the object, but the matching is actually done in full 3D pose, in 6D pose space. Okay, here's on the T-less data set, we can also see that it works actually very well on these less textureless kind of objects. On ModelNet, we also showed that for these kind of objects, we can use this approach to match actually unknown objects. Okay, so we can train DeepIM on objects from certain categories, and we can then on many objects, and then we can apply it. The caveat with this work is that transition to unknown objects, we haven't been able to get to work very well on real data. So this works on reasonably simple examples such as ModelNet. Here's an example. You can also now use this DeepIM technique for tracking, right? Because you just initialize the next frame with the previous frame estimate and then continuously do this re-rendering and optimization that DeepIM is doing. So what you see here is a sequence of this yellow mustard bottle, and you can see the more intense color is where the reprojected image is shown into the video sequence here according to the DeepIM estimate. So you can see that at this point it's actually keeping track pretty nicely even of these reasonably complicated rotations. When it's getting highly occluded, of course, the estimate gets a bit worse, as you can see here, but it's not getting totally lost, and it pretty quickly snaps into place once we can observe the object again. Okay. One very quick note is, so DeepIM uses exact 3D object models, right? So it requires object models to be available. One paper that Hyunhong Park just presented yesterday at CVPR, it's called Latent Fusion, is trying to get away from the notion of requiring exact 3D object models. So in this work, he showed that by just taking a set of images of an object, okay, and registering them using standard image alignment or structure for motion kind of techniques, we can then feed those into a pre-trained network that along with the registered poses, such that we can map that into a latent object space, which is a 3D voxel space, where in each voxel we store these latent features, such that this latent object model can be fed into another network that takes the latent object model along with a pose, and it will render from that pose view a predicted depth camera images or even a predicted color image. Okay, and we can now use that and compare it to an input image, to a query image, for example, from a depth camera, and then can do matching using this network. So since the network is, of course, differentiable, in this case, the re-estimation of the pose is just done by the gradients coming through this pre-trained network. Very, very importantly, this network does not assume any pre-training or any training on the specific objects. It's pre-trained on many images from ModelNet and ShapeNet, and then can be applied to a new object only by putting in, let's say, a set of images. I think that's a really important step forward. And we're getting on LineMod, for example, it's getting results that are very close to the results that DeepIM is getting with full models. Okay, so here on the right, you can see now, for example, such a matching process. All right, and with that, I'm coming to the end. I talked about in robotics how we can apply matching in the context, for example, of navigation object pose estimation. I showed how we can build kind of a full navigation system that is solidly based on image matching, if you think about it, right? So there's one aspect of just matching images where we control the robot to reach a target image. Another question is match overlap estimation. How similar are these images? If we can do that, we can use kind of that for the navigation process. Another important aspect is match, what you might call match success estimation. Like given two images, will we be able to match them? So predicting that, and we can use this for loop closure, for example, loop closure and sparsification of the data. And then matching in the context of object models, of course, is that I think these iterative matching processes provide significantly higher accuracy than systems that just try to regress immediately to a 6D pose. And again, there's some other work that I wasn't able to mention. But in the interest of time, I'll leave it at that. And I'd like to thank specifically the students and interns at UW and at NVIDIA that worked with us on this project. And of course, the main research scientists at the NVIDIA lab. Thank you very much.
Thanks a lot. Thanks a lot for the great talk. So we should take some questions. There's some time. So first one, actually, I had a quick question. So the system you presented with the waypoints and the navigation. So I assume that this obviously needs to train in each specific scene, right? But the good thing about the standard local feature approach is that you can just have it work everywhere. Do you have an intuition about when we can go to methods that can be applied to a new building or a new scene or something different?
Yeah, that's a good question. Also great that should I turn off because I can't see any, oh no, this way I could see at least people. Okay. So there's 2 points here. On the one hand side, what we do need is these, let's call them mapping trajectories, right? We need kind of traces through the environment to build this map from. And we haven't looked at how to guide the exploration, but we're actually investigating that as well. But the matching or any of this is totally independent of the environment itself. Okay, so that's important, which means the local controller, the high-level controller, the reachability estimator, they are all being applied to unknown environments. Okay, so the only thing we need is a map itself, right? But the matching process itself is independent of that. And what I found surprising actually that it works pretty well, even if trained in Gibson simulation and then in the real world.
Okay, thanks for the answer. There are some questions from YouTube. So how do you apply Dijkstra's algorithm with the reachability estimator? It would work if the cost was additive, but it's a probability measure, so it should be multiplied along the path. That's the question.
We're optimizing the log probability, and then it's a sum.
Okay, another one is...
so the max is still the same then, right? And that's what we're doing there.
Okay, another one is, have you looked at the object pose estimation like in DeepIM, when the object 3D model does not have texture, but just geometry?
Yes. I think we have. So on the one hand side, of course, there's like the TLess data set, which has far less texture. And I think typically what you want to do is you want to train it then on objects that have less texture. And the nice thing is, because it's trained in this, let's say, more holistic way without key points, right? It does actually learn to match these objects, even if they don't have any specific key points. So for example, in the YCB data set, there are objects like a bowl, a red bowl that doesn't have any texture on it, so zero texture on it, and we can still match that well. Because again, the system learns to do this in this more holistic way.
Okay, we have a couple more. So what is the speed of DeepIM in case that it needs rendering for each iteration?
The speed? Was it the question?
I
don't know exactly, but it's like, yeah. You could say, but it was like, I think like 5 to 10 frames a second. So it works in real time.
Okay.
And now I'm sure we could optimize it further. And with the most recent super cool NVIDIA GPUs, of course, we could make it certainly fast.
Yeah, we have another one. How do you ensure that the controller training data is balanced in terms of commands? For example, navigation is often dominated by forward movements.
Mm-hmm. That's a good question. And I think Sheng-Yun could hopefully answer that. But I think what he mostly just did was randomly in the map sample or start configuration, end configuration, and then navigate along that. And even if it's not fully balanced, but since the input to the low-level controller is this waypoint relative to it, right? So even if you're sampling more of the, let's say, waypoints that are kind of in front of the robot, but since the controller is conditioned on it, it typically works pretty well. And since these environments have many obstacles in them, it happens pretty often that the robot does actually have to make turns and things like that.
Okay, thanks a lot. I think that was all of the questions we had now. We tried to do virtual clap for Krystian before, and we had some technical issues, so we'll do a clap for both speakers.
The old-fashioned way.
Thanks a lot for the talk. And passing on to Eduard.
Yeah, okay. So now we move on to the two poster talks. The first one is two-stage discriminative pre-ranking for large-scale landmark retrieval by Shuhei Yokoo. Shuhei, if you are here, you can try to share your slides.
May I share my screen?
Yeah, you can do that. Okay. And I want to say thanks for showing up, everyone in particular, but especially for the people who are in Asia, who have a really complicated time zone. It's the middle of the night right now, but thanks. So this work, I think you can just talk about it.
All right.
Yeah, you can go on.
Yep, this work is, I'm going to talk about our work, two-stage discriminative ranking for large-scale landmark retrieval. And this work is done by presenter Shuhei Yokoo and Kohei Ozaki, Eduka Shimosera, and Satoshi Iizuka. This is a summary of our main contributions. We construct effective pipeline for high-quality landmark retrieval. Our pipeline employs data cleaning using image matching and ranking approach based on exploiting label information. And we provide strong baseline for Google Landmark Dataset V2, in short, GLD V2, which is huge, diverse, and noisy dataset. This dataset benchmarks the performance of image retrieval and fine instance-level image recognition, and we achieved first place in the Google Landmark Retrieval 2019 challenge based on our pipeline. Before describing our method, I'm going to take a look at Google Landmark Dataset. Google Landmark Dataset, GLD, is the largest dataset of instance image retrieval, contains photos of landmarks around the world. GLD has two versions named GLD V1 and GLD V2. These are both large-scale datasets, but later GLD V2 is more challenging in various aspects. The first reason that makes GLD challenging is that its huge scale. The number of samples of GLD V2 is more than 4 million with only train set, and the number of labels of GLD V2 is more than 200,000. And label distribution is extremely long-tailed and highly imbalanced. And large intra-class variability. In extreme cases, outdoor and indoor images are labeled as same label. And considerable amount of noise. This is an example of a set of images with same landmark ID. As you can see, it includes images that don't seem to be relevant. So we tackled these challenges by data cleaning using image matching and ranking exploiting labeled data. I'll give you a quick explanation to review the overview of our pipeline here. First, data cleaning is performed on GLD V2. And then GLD V1 and the clean version of GLD V2 are used for training of ResNet using arc phase loss. Arc phase loss is one of the methods of metric learning used in face recognition, but it turned out to be useful for landmark recognition as well. The trained ResNet is used to extract a global descriptor, which is then used to perform k-nearest neighbor search to retrieve similar images. Finally, our ranking is performed to refine initial retrieval results. First, I'm going to explain about data cleaning part. Motivation of data cleaning is this. As I said, GLD V2 is very noisy dataset. So we want to alleviate learning a global descriptor from the adverse effect of noise. So we developed an automated data cleaning system inspired by work of landmark screen dataset creation using depth and spatial verification. Depth is a local descriptor based on convolutional neural networks. It outperforms classical methods such as shift in landmark recognition. And spatial verification is a method that verifies two images, checking the spatial consistency of them, performed by local feature matching with Lanczak. If the count of inliers is greater than certain threshold, two images are regarded as verified. I'm going to explain about our proposed automated data cleaning. Our method consists of multiple steps. First, for each train image xi, we get k-nearest neighbors from the train set. In this step, we use global descriptor already trained with JLDV1 for k-nearest neighbor search. Second, we select up to the 100 nearest neighbors assigned to the same label to xi. By doing this, we can reduce the number of times of spatial verification, which requires high computation. This point is the main difference from data cleaning of creation process of landmark screen, which exhaustively doing spatial verification among all samples within same class. Then we perform spatial verification on up to the 100 nearest neighbors. In spatial verification, we use Lanzac and Delph as local descriptor. Finally, we add xi into our cleaned subset when the count of verified images is greater than the threshold. By those steps, we can build a cleaned subset. We are successful in cleaning the dataset. However, this has a side effect of reducing the available training data by 1/3. Despite this, as we will show in the next slide, results on the testing set improve despite less available training data. In addition, image retrieval performance improved a lot by training ResNet with cleaned dataset, indicating a high presence of noise in the original dataset. Next, I'm going to talk about ranking part. The motivation of a re-ranking is how do we retrieve landmark images that have diverse appearances, such as exterior and interior images. For example, the rightmost image is the same landmark as the query, but it does not hit the ranking due to their visual dissimilarity. These images are extremely hard to identify as a landmark without any context. To solve this, we propose a new ranking method, two-stage discriminative ranking. The key idea of our ranking method is using label information as bridge. We aim to retrieve hard examples through this bridge. Then, how to exploit label information? We leverage KNN classifier prediction for re-ranking. We divide samples into positive and negative samples. If a sample from retrieved images is predicted same level as query image, we treat this as positive sample. And if not, we treat this as negative sample. And then we make positive samples ranked higher than negative samples, considering that positive samples are more relevant than negative samples. Note that these KNN prediction can be performed offline manner except for query image, and thus heavy computation is not required in online inference. This is an outline of our ranking. This table is experimental results that compare our ranking and existing ranking methods. All the results are based on the same KNN search result shown at the top row. We show that our ranking method outperforms existing methods if label set are provided, because our ranking method can leverage label information while others cannot. Note that we didn't experiment on R-Oxford or Paris in ranking because these don't have labeled set. This is the qualitative results. The bottom row shows our search results. Compared to the existing ranking methods, ours are able to hit even difficult samples. Finally, I would like to talk about the main contributions of our work again. We constructed effective pipeline for high-quality landmark retrieval. Our pipeline employs proposed data cleaning and re-ranking approach. And we provide strong baseline for Google Landmark Dataset V2, which is huge and diverse and noisy dataset. Thank you very much.
Hi, thanks for the nice presentation. I have one question, which is, what do you think was, you actually won this challenge, which is a very popular challenge and gets many submissions. So this is quite impressive. What do you think helped the most here? Is it cleaning the data? Is it the re-ranking?
First, thank you very much. And what's the most important part of our submission is, I think these two, data cleaning and re-ranking, is similarly contributed, I guess. But in terms of score, re-ranking is suitable for these situations of GLD V2 challenge. So in terms of score, re-ranking is more contributed. But yeah, I think these two are similarly important.
How much do you think label noise, this is a question from Vassileios, how much do you think label noise affects the re-ranking? Because you still have some label noise, right?
Your question is how much ratio in the noise?
So how you still have noise in the labels? How do you think that affects the re-ranking? I don't know if I'm asking this correctly.
Sorry, I couldn't catch your questions. Maybe I guess you asked about how is the noise images affect the re-ranking, right?
Yeah, I think Vassileios can clarify 1 second.
Yeah, basically, yes, there's wrong labels inside this big data set, right?
Yeah.
And how much this affects the re-ranking? This is the question.
This is a difficult question because I think the noise is harmful for re-ranking because in our re-ranking we use KNN classification, so noise can degenerate the accuracy of KNN classifier. So and it leads to also degenerate the re-ranking results. Is it okay? Does it work?
Yeah.
Yeah, I think that's clear. Okay, thank you. Let's thank the speaker.
Thank you very
I'll just
much.
do it myself. Yeah, can you stop sharing the screen, please? Our next presentation is match or no match, keypoint filtering based on matching probability by Alexandra Papadaki from the Technical University of Berlin. Alexandra?
Yes, hello, thank you. I'm Alexandra Papadaki. Do you hear me?
Yes, it's fine.
Okay. So I would like to present you our work called Match or No Match, Keypoint Filtering Based on Matching Probability. I will share my screen now, and I have to close my camera, unfortunately, because of internet connection. So this work was performed by me, the presenter, Alexandra Papadaki, and also Ronnie Hansch. So one of the biggest problems regarding the computational cost and accuracy in many computer vision tasks, like key point matching and 3D reconstruction, is the large amount of unreliable key points, especially for large-scale applications. These are usually caused by difficult capturing conditions and error-prone areas like those shown on the image here, with vegetation, repetitive patterns, moving objects like pedestrians, and homogeneous areas. This can be handled by reducing image pairs, improving descriptors and matching, and filtering matches. In our case, we reduce the key points, like the similar work of Hartmann et al. 2014, using a binary random forest classifier. However, here we use simple key point properties as training features instead of the SIF descriptor elements. The Hartmann et al. Method, though, was used as comparison method for the proposed one. For that reason, the main goals here were to filter out non-matchable key points and preserve matchable ones in order to improve matching and 3D reconstruction in terms of accuracy and time efficiency. For example, as shown in the image, the final goal was to avoid the red points on the error-prone areas and keep only the green ones. How did we manage to do this, though? We introduced the problem as a two-class classification between matchable and unmatchable key points using a random forest classifier. In fact, we suggest 8 pioneering training features that are simple enough to compute, but capture geometrical, textural, topological, and appearance properties. These features are the image coordinates, the size, the orientation angle, response, octave, number of dominant orientations, and the green channel intensity of the key points. More sophisticated features were also examined, but they only added to the complexity and not to the accuracy of the algorithm. The graph here presents the whole workflow of the proposed method. As shown on the left, the training data are obtained offline using a typical SIFT-based structure for motion pipeline. SIFT was chosen because of its performance, but other detectors could also be used if the required information for the features is provided. The detected key points are matched based on the L2 distance between SIFT descriptors, followed by a ratio test, a symmetry cross-check, and outlier removal via RANSAC. The random forest is trained on the obtained matches and key point features. Then it can be used to pre-filter detected key points in a new image based on their predicted probability to be matchable. So then matching is only performed on a small fraction of all key points for which the corresponding matching probability is high. Many experiments were performed to evaluate filtering, but also its actual impact on subsequent computer vision processes, since a good classification performance does not automatically imply good performance in subsequent matching or other processing steps. The tests were done on various stereo and multi-view datasets depicting building facades. We used 150 training images and more than 400 testing images. The images were captured under different conditions, depicting different types of buildings and including error-prone areas, which were successfully handled by the algorithm. As mentioned before, we suggested a set of 8 training features, which are evaluated according to their mean decreased accuracy or else permute importance, as well as the selection frequency. Both methods measures suggest that the size, color, and the number of dominant orientations are most important. Response and coordinates have a medium importance, while octave and orientation angle are less important. However, all features contribute to the final performance without decreasing the accuracy. And also, the small number of features allows a well-performing and fast classifier, which does not require a huge amount of data. Let's see now the actual filtering results. We see the detected points in red and those that survived classification in green. Solid green circles represent those that were finally matched. So the proposed method filters out many of the red points that lie on error-prone areas like pedestrians, repetitive patterns, vegetation, and homogeneous areas. For the rest of the analysis, we compared the proposed method to the standard procedure without any key point filtering, as well as to filtering as proposed by Hartmann et al. All experiments are performed using identical data, procedures, and hardware. According to the recall, the proposed algorithm manages to preserve 73% of the matchable key points, and also according to the specificity, it filters out 50% of the non-matchable key points. The low precision and medium accuracy are mainly caused by the unbalanced data and the survival of a lot of non-matchable key points. This, however, has no effect on the objectively good performance on preserving the matchable key points. The other method filtered out slightly more non-matchable key points, losing though a few more matchable key points. However, a good filtering does not guarantee a subsequent good matching. Since the classification is performed independently for every image, it is possible that essential matches are lost if the corresponding points are not preserved in both images. Comparing the matches, though, the proposed method preserves 73% of good matches and avoids mismatches, like, for example, on the repeated identical columns on the top of the building shown in the images. The proposed prediction is 10 times faster than the algorithm proposed by Hartmann et al. This is mainly because of the fast-to-compute features and small architecture of the random forest model. Pairwise matching, as shown on the right, is accelerated by approximately 35% for both filtering methods compared to the standard matching, which is shown in black. It should be noted that filtering time grows linearly with the number of images, while matching cost grows quadratically. So, for larger image collections, the performance benefit could be higher. An evaluation in an end-to-end structure from motion and 3D reconstruction pipeline was also performed using CallMap software and multiple multi-view datasets of around 20 to 100 images. The proposed algorithm reconstructs more accurately and completely the 3D scene compared to the structure from motion without filtering and the structure from motion with filtering as proposed by Hartmann et al. As shown in the histogram, the proposed method achieves smaller projection error while reconstructing much more scene points. In fact, in this example here, the proposed method reconstructed 32% more points than filtering based on Hartmann et al. This large difference comes mainly from the rightmost facade, which is missing or mismatched to the center facade by the second method. The wrongly reconstructed points are marked in blue. The proposed method also reconstructs more precisely the ground truth geometry, even if using a single stereo pair. The challenge in this test was to reconstruct the 90-degree corner of the depicted building. A reference point cloud, shown in blue, was created by using 30 images of the whole building. The rest point clouds were created by a simple stereo pair. The lower part of the figure shows a horizontal slice for easier interpretation. It can be noticed that the only point cloud that reconstructs the two facades as being orthogonal and coincides with the control point cloud is the one produced by using the proposed filtering, shown in green color. Point clouds produced by the filter by Hartmann et al., shown in magenta, and no filter SFM, shown in orange and red, fail to preserve the geometry, providing much wider angles. So the proposed method, except for improving 3D reconstruction accuracy, precision, and time efficiency, it also manages this, requiring less data. Concluding, we proposed a key point filtering method prior to matching by training a very small 5 trees with depth 5 random forest classifier with 8 simple features. The method successfully preserves 73% of the matchable key points and filters 50% of the non-matchable, especially those on error-prone areas with vegetation, repetitive patterns, moving objects like pedestrians, as well as homogeneous and textureless areas. Consequently, it improves matching by avoiding matches and accelerating pairwise matching by more than 30%. Finally, it increases significantly the accuracy and precision of 3D reconstruction while requiring less data. Thank you very much.
Thank you for the nice talk. We have one question on chat. Let me read it. Does your filtering criteria take into consideration the number of features per region or grid, or just filters them regardless of the neighboring points?
Excuse me, can you repeat?
Yeah, you can, if you have YouTube open, you can check it there. Otherwise, I'll just repeat it. So does your filtering criteria take into consideration the number of features per region or grid, or it just filters them regardless of the neighboring points?
No,
I guess it's just, so go on.
No, we examined the in-image similarity, in fact, as possible features that could be used for the training, but we figured out that it's not really helpful regarding the accuracy. It was rather adding to the complexity. And
okay.
Kind of points, yeah.
I have one additional question at least, which is, so some of the, I'm going to call them cues that you fit into the classifier, I don't know if they are normalized or not. So for instance, X and Y obviously depend on the size of the image. The scale also depends on the size of the image. The green color channel depends on the general brightness of the image. So did you try different strategies? Is this normalized and normalized?
No, we use the images as they were, and the coordinates are absolute image coordinates.
Okay. Did you have like a constant image size, or do you have images that are like landscape and portrait?
We had both formats, landscape and portrait. The dimensions were more or less the same with same LSR. Digital camera, but yeah, the dimensions of the images were about 5,000 to 3,000 to 4,000 pixels.
Okay, thank you. I think that's it for me. Let's send the speaker. Thanks for the presentation. I think Kwang will take over now.
Sure, 1 second. All right, so this is a little bit funny because as you see in the title already, it's reintroducing the image matching benchmark. Last year we tried to introduce, but then we had some interesting events, for example, the power going out. So this will be actually the introducing, but then again, it's reintroducing. Without further ado, I'll talk a little bit about what we did for our challenge here. So the question that we're interested in, if my slide will go, is how good your favorite method is in practice. So we want to emphasize a little bit here about in practice, because in fact, we had some difficulties using existing benchmarks, and that was actually the main motivator for our benchmark here. So as Krystian actually mentioned in his keynote before, much of these type of benchmarks exist, which accelerated the development of local learned descriptors quite a lot, are becoming a little bit saturated. So if you look at how the methods perform nowadays, we are really at a level where our false positive rates are below 1% and perhaps even going up. And it's quite interesting that new methods are going up, given that they are published for a reason, showing that their methods are actually performing better on a certain metric, meaning that this benchmark is becoming a little bit outdated. It's a great benchmark for training, though. And this also is in line with our experience in 2016, where we published a paper called Lift. And what we did was we evaluated performances of all the entire local feature pipeline in terms of something called matching scores. And when we did that, it turns out some of these descriptors that are claiming to be better actually work better on the UVC data set, But in case of matching scores and other data sets, that wasn't really the case. So there was this gap between what's reported in that data set versus what we actually have in practice. So of course, it's not only us who noticed this. It's actually one of us. It's Vassileios' paper on benchmark. There was a step towards making this more rich and rigorous. And it's called 8 Patches. It's a wonderful work. You should, if you haven't checked it out, you should go check it out. It's also work towards this direction of having a proper benchmarking of these local features. And of course, since just stereo setups were limiting, there was also work towards benchmarking in structure from motion pipeline here. So one thing about this work was this is great, but then in this work, it was using phototourism data. So there's no actual ground truth to compare against. So the metrics that were suggested on this work was related to how the structure from motion outcomes look like with some proxy matrix, such as track length and such. And the difficulty really comes from ground truth. So if you can actually have very, very accurate ground truth by using LiDAR scans or these kind of control setups where you get depth. But then that comes at a price, right? So as you see on this, for this example, you're actually measuring with a single camera with sophisticated equipment to do this. And that's not easy to do for massive real world data sets like phototourism data sets. And there were other data sets that also were towards this direction of things working in practice. For example, there was a workshop in this CVPR as well a few days ago, which has focused on localization. In their case, it's really all about localizing with different weather conditions, long-term conditions like night and day conditions. But in our case, we were more focused on how local features and metrics work in a wide baseline stereo and a structure from motion setup. So I think I teached you quite a lot already. And what we want to do is this. So while trying to form a benchmark, we ran into two main issues. One was that image matching is modular, although this might seem very, very natural to people who worked on image matching from back in the days. But the bottom line here is that it has so many moving components and it's very, very tricky to really do benchmarking properly. And you need to tune it. We'll show later, Dmytro will actually talk about this later in detail on how impactful this tuning process is. And another problem is, again, as I mentioned earlier when I talked about SFM work, there's no ground truth. So we want to use various data, but using various data types from the internet comes at a cost that we can't go there. And we can't ask people who took those photos to label these places where they took the photos accurately and such. So our work basically goes towards like this. So we, of course, it's modular. There are multiple components, but I'll just introduce the two key insights that we put in. So the first insight is that, well, if you have enough images and enough large set of data, off-the-shelf methods are mature enough to give you very good results. So for example, if you have hundreds to thousands of images, you get reconstructions with SIFT or even with more recent methods, you'll get a consistent reconstruction that works quite well. And then, of course, that's a very easy problem. But then if you reduce the number of images that you put on a certain pipeline, that becomes harder. And now we could actually measure how the harder problem solution relates to the easy solution. And that's how we create our pseudo ground truth. And another important thing I want to emphasize here is that what we do, we always evaluate based on downstream tasks. So we don't want to restrict ourselves to matching scores or repeatability or those metrics that are aiming for individual component evaluation. We want to see how well these things actually work when you estimate the camera pose or when you construct 3D maps. So our data set, as I hinted earlier on, is phototourism data sets. We collected all, we basically make use of the already available phototourism data sets that are out there. And then we constructed a 3D map. I want to give a bit of a shout out to Eduard on this because I saw him eating up our compute cluster for weeks, just creating SFM maps with all the pairs that are possible with these large data sets. And that's how we get very, very accurate ground truth. And those look like this. That's not a bad reconstruction at all, considering that you get these images from the internet. And of course, we had to validate this. And we did validate the quality of constructions by looking at the pose difference as you increase the number of images or that you subsample from each data set. And basically, the bottom line is that they get reduced. They're already quite stable after 200 images. And regardless of which feature that you use, we see the same phenomenon. And of course, we did compare reconstructions between different Keypoint and different methods, and they also seem to coincide very well. And one thing here is, for example, SIFT and R2D2, they're at a level where our evaluation metrics are designed to ignore. So they're less than 1 degree in terms of rotation translation error, which is quite accurate. And I forgot to mention that we also had a look at our data with our eyes, with all the projections for hours, trying to figure out if there were inconsistent matches. So this is how our data looks like. We have our training data composed of a lot of sequences here. I forgot to count on top of my head, but it's about 25,000 registered images. And as long as it doesn't overlap with the test data, you're free to go beyond the training data that we provide. And this is the test data that we use. These are some of the scenes. We have 9 different scenes. We use these images to reconstruct. Then we randomly subsample 100 image pairs, which we use to evaluate the poses. And for SFM, we again subsample images to make harder pairs composed of 5, 10, or 25 images. And that's how we evaluate the SFM reconstruction performances. So now, probably the biggest question for those of you interested in sending your methods to our challenge or the leaderboard would be how to actually submit it. So we have a bit of multiple ways that you could actually submit, because our benchmark framework is modular. That means you can plug in your algorithm at various steps. For example, the first thing that could be is that you're only interested in evaluating your local feature performance. Then that's also something that you could do. You could just extract your features, provide them to us, and then we'll process the rest. We'll do matching, outlier filtering, and everything. And of course, you can specify which of matching and filtering method that you want to use. Or if your method is something that involves a particular type of matching, for example, you have something particularly designed for your method or descriptors to filter out matches or some different matching strategy, you could also provide that yourself. And then we do the rest again with RANSAC and pose estimation call map. No need to run it for yours on your side. We could just run it on our side as well. And of course, for learned outlier rejectors or learned matchers, you could also provide them here at this stage. And then we'll use your initial matches, or if you want, we could disable RANSAC and use your matches entirely to get the pose error. And we could then use those as your leaderboard entries here. And we've been saying this from last year, sorry, but we are planning to do post submissions. Probably after the workshop, we'll get to it and then implement it and release it as soon as possible. So these are some of the things that we report. So in our benchmark leaderboard page, which I'll show you soon, we report these mean average accuracy. So we used to call them mean average precision, but it turns out that was a misnomer. So we're calling it accuracy because we don't have any negative results. And what we do here is we look at the average accuracy of the poses using degrees under a certain given threshold, and we look at the area under curve. And this is the average value here. And of course, if you're interested in more traditional metrics, we also have repeatability and matching scores. But one catch here is that we are not using the traditional overlap threshold here because some of the methods do not provide their support regions. We just simply look at the 3-pixel threshold after using 3D reprojection. And other traditional, more SLAM geared towards SLAM metrics are also here for SFM. And these are, for example, track length, average trajectory error are also provided. But to keep things simple, we look at the mean average accuracy as well on the multi-view case as well, which we compute by using multiple pairs that all the pairs that are within a SFM reconstruction. And then we combine all the metrics by just averaging the stereo and the multi-view results, which is actually the number that we use to rank each method. So basically one number to rule them all. We wanted to keep it as simple as possible. So here's a very wordy slide. Probably would be most useful for you guys when you later on look at this presentation and just pause it. We'll also probably release the slides. So you can click on these links later to get details on the exact repositories. But the bottom line is that we have our benchmark already open source. It's based on Python. And you can also have a look at the examples that you have for importing and using your own key points using these benchmark baselines repository as well. We implemented our matcher using PyRansack, and Dmytro will probably talk a little bit about that. Or if you're interested, you can look at the paper that we have. Basically, we warn against using OpenCV Ransack. And so we also provide some wrappers around learn matchers. We have the Learning to Find Good Correspondence paper, but we're planning to include more as we go on. That's the beauty of open source. And we also release a parallelized job scheduler that you could use using GCP. And all these things that we released run in parallel, but you could also run in sequential by just plugging in an option here. OK, so so basically all you need to do is provide the features or matches using an H5 format, and then you provide a JSON file that encodes what we're supposed to do with it and some metadata related so that we can actually contact you if something goes wrong. And you just need to run it, and it will take a while. But once you run it, you'll get the results reported just as we have on our website. And the submission, if you're still unclear about the submission instructions, we did put up this clear set of directions on the website. Do have a look. And upload server is password protected. We might actually have to update the upload server in a while, but it will always be updated on this web page, so do have a look there. And please keep in mind that don't spam too much with like daily submissions. We do have a limitation on how many submissions are allowed per week. That is because we actually use roughly 100 core years for this year so far on Compute Canada alone to just compute all the benchmarks here. So it is resource demanding. So we have said in our challenge, we now have two main categories for number of features. We have the restricted and unrestricted categories. The unrestricted is up to 8,000 features per image because we are, otherwise it takes just too long to compute. It becomes quite impractical. And we have multiple descriptor sizes. We have the regular size set to be the sixth descriptor size, just because we wanted to keep this benchmark in line with what we were doing from the past. And the results are updated frequently, and they actually look like this. Let me show you this website if I can. Apparently, yes, that worked. So this is the leaderboard page. It shows you all the results. I should have masked this, but that's a bit of a spoiler, but it's fine, I guess. And you will be able to sort through the results with whatever metric that you want to look. But the interesting thing is if you click on these entries, you're also able to see some detailed outcomes. For example, results of a given method on a given each of these sequences, and also how it compares with other methods in a very detailed area under curve scenario, per method, or average accuracy values. And much of these things are interesting. And we also provide visualizations here, so you can actually look at the leaderboard to get some detail on the pros and cons of each method. And yeah, for example, like you could also see some of the matching results. So fun fact, since we were verifying these pairs for these symmetric landmarks as well, so we had a bit of a trouble trying to see if it's north-facing or south-facing. But I think I became an expert on recognizing whether this is north or south, because there are small subtleties around the environment which allows you to actually do this. So although it looks symmetric, this is doable if you train yourself for a long time. So that's about our benchmark. And I think I'll, without further ado, pass it on to Dmytro so that he could talk a little bit about our findings from the benchmark framework and the paper that we published, well, not published yet, pushed on arXiv.
Thanks. Can you share your screen, please?
Yes, 1 second.
Okay. Okay. Sorry. Okay, here we go. Hi. I'm going to present like all our findings which we did for benchmarking the methods which were online available, I think, up to March this year. So, and we have found kind of a lot of interesting results. Some of them they are small, and some of them they are actually huge, at least in my opinion. So let's go. So there are a lot of components in the image matching module, and I am going to start from the last one, from the most overlooked part, because actually in like yesterday's oral session, I still have seen that someone used sieves plus no name ransack, and we are going to show that is kind of a wrong thing to do. So, and I think a year ago, I posed this Twitter poll. So what do you use? OpenCV ransack, obviously. And this is not the best idea, actually. So what did we do? We take sift features, take optimal matching for them, and then hard code to the maximum confidence, like 0.000099999. And just vary then maximum iterations number for different ransacks. And as you can see that OpenCV ransack does not perform very well. And the worst only is SK image ransack, which is here, but it's just because this is super slow, because it is implemented in pure Python. And the modern ransacks are much better. Moreover, it's very important how do you set up the parameters like inlier threshold for the runsacks. And by the way, here are the link where you can put the, like, we use proper runsack. Here are maxsacs, which is one of the best one, and degensack, which is can be installed via pip without any compilation needed, or GC runsack, and so on. So let's go now. Then it's interesting that you need to tune whatever runsack do you use for each local feature and per each matching method. So don't look at the local features, what is the better yet. I will go to this. But what's interesting is that optimal threshold is different. Okay, so this is, oh, okay, here I have these numbers. So for example, for GC runsack, for lots of features, the optimal threshold is half of pixel, which is kind of fine. For another method, it is like 1 or 1.5. And for other runsack like maxsack, actually optimal value is 2 or 3 times more. So you just cannot say, okay, I pick some threshold for feature, the same for all features and the same for all runsacks. You actually can manipulate in your paper with malicious or just because you don't know this intent, that you can make almost any feature win or look better or worse depending on inlier threshold which you use. And it's kind of natural that methods which are not as precise in repeatability like D2Net, they favor bigger inlier thresholds and more fine-grained methods like SIFT with quadratic interpolation for subpixel. You can put some quite strict threshold. Okay. And here, just for you to understand what are the difference for the optimal values, this is numbers. And for the same feature like SIFT, optimal threshold can go from 0.25 to 1.25. You also need to tune matching and so on. So it is very, very different, and you cannot use just one value if you want to compare something. For practical reason, yes, you can pick something like 1 on 0.5, which should work well for wide number of methods, but still it would not be optimal. So after we have so cool toy, actually, and after the submitting our journal paper, a lot of people wrote to us in private and email and say, why you haven't benchmarked our cool runsack? And we have only tested maxsack, degensack, GC runsack, and OpenCV. And answer was, okay, we have benchmarked only those which are available to run in Python. So no Python, no benchmark, sorry guys. And then after we have some time, we say, okay, and Daniel was willing to actually run C++ method, and I running them for this machinery. And we actually benchmarked a bit more runsack, which I'm going to present now. And it was presented on runsack tutorial. So we added USAC, which is often seen as kind of Uber, like the best runsack you can have, and a contrary runsack, which supposedly you can survive without setting any inlier threshold. You just set something and it's good. So let's see how well it holds. And by the way, we also evaluated a lot of learned methods, and we provided them the same exactly correspondences, which are root sift features with optimal matching. And how all these methods can filter them out. We haven't included SuperGlue, which we know work pretty well, but it takes a kind of much richer input than just correspondences. It uses like all keypoints, all descriptors, so it kind of not fair to compare. And so we benchmarked quite a few learned methods. So how it works? So for classical methods, one thing is, so OpenCV is bad. This locally optimized Ransack is better. So Degensack is much better than OpenCV Ransack, and again you can see that is from 0.35 to 0.45, so it's quite a lot. So GraphCut Ransack and Degensack and Maxack, they're working pretty well, and this is from 1K iteration, so this is like super fast regime. And usually if some Ransack is better for some angular threshold which is strict or which is very loose, it's going to be better for all the across the threshold. So our metric is kind of consistent. Now, if we increase number of iterations for 100K, and here is a contrarian Ransack, which without tuning the threshold basically doesn't work. So you need to tune threshold for even contrarian methods. Here is USAC, which is not the worst Ransack, but still is much worse than Degensack or GC Ransack or Maxack. So please don't use OpenCV Ransack or USAC as a kind of the best Ransack in your paper to show how cool deep learning methods are. So use some fair competitor like state-of-the-art Ransack. And here is how learned methods work with Ransack. So this is if you're applying just methods like CNE, OANet, ACNE, deep fundamental metrics estimation without Ransack running. So it does not work as good as running just some handcrafted thing plus good Ransack. But if you add for this learned method some state-of-the-art Ransack, you get quite maybe small but nice improvement. And this is how all the leading methods in our competition actually have their big places, just because they combine the state-of-the-art Ransack with their state-of-the-art deep learning filtering methods. So the take-home messages for Ransack part that you cannot just use non-robust estimator. You need to use both Ransack and deep learning methods. And again, don't use OpenCV Ransack. And claim that some methods are parameter free and you can just run with any threshold. They doesn't hold in practice. And again, you need to tune Ransacks. Now, matching and filtering. So one thing which is widely overlooked, at least until very recently, that for deep learned methods, like for deep features, people just use simple nearest neighbor matching and just output this raw nearest neighbors as a kind of result of matching. And this is a very bad idea. So if you're using matching, you need to filter them out, and unless you're using some deep learning filtering methods, use this lower ratio test. And the best one is to use actually in both directions. So you require that matches, and this is this green one, that matches nearest neighbor should be consistent in both directions, and you apply first the second nearest neighbor ratio, and it works the best. And it also shows that with more features you have better results. So we pick 8K features and 2K features for our competition. Also, this strategy of mutual nearest neighbor and ratio test is the best, works the best for the binary features like OR, freak, case, and others. And even they are traditionally used with just Hamming distance, which is descriptor distance. You have threshold on this, and if your nearest neighbor is far more distant than there's your, say it's the wrong match, and then if it's closer, you say it's correct match. And these are these blue curves. And if you use second nearest criteria, everything improves. And it's actually not that computationally expensive to use, so please use this. Additional thing, if you have multiple orientation, or you have like very small non-maximum suppression window, you can have your second nearest neighbor very close to your first nearest neighbor. For example, here on this like classical image of bikes from Oxford dataset, you have green one is correct nearest neighbor, and second nearest neighbor is just the same Keypoint location, but with different orientation because of symmetry. And because of they are very similar in descriptor space, the second nearest neighbor ratio might kill it. So is it really a problem or not? It turns out that actually not if you're doing tuning. But if you don't do expensive tuning for the matching threshold, you can use for geometrically inconsistent criteria, which is take the second nearest neighbor, which is far enough from the first nearest neighbor in pixel space, like it's like literally outside that 10 pixel radius. And here is this dashed line. So you can see that it's kind of wider optimal area, but the tuned maxima are quite the same for the learned methods like HardNet or KeyNet HardNet or SIFT. So one more thing which we discovered is this is approximate nearest neighbor search is not for free. If you use FLAN, which is very popular thing in OpenCV, and use OpenCV default, this is a yellow thing is on H patches, and I will show results on our benchmark in the moment. This is exact nearest neighbor, so quite huge difference, I would say. And this is if you tune your FLAN, you can actually be quite close to the accurate nearest neighbor, but which is more costly to compute. Although now with phase, you can compute this very efficiently on GPU. So, and it works for both HardNet or SIFT. So don't use OpenCV defaults, at least don't trust them, check if they are good, and don't use blindly approximate nearest neighbor search. And here are results on our benchmark. So you can have up to 20 relative % of mean average accuracy loss for D2net, which is not that great originally, and it's even worse. You can have a quite significant drop in accuracy for HardNet or even SOSNet. And what is actually important for the benchmarking, that it's order of the results is changing. So SOSNet is actually better descriptor in exact space, but if you use FLAN, then actually it is kind of worse than HardNet. So surprisingly for SIFT, it's not that huge problem, but still you lose some accuracy points. Now about local features. The best on, okay, and these guys are on the, I guess, validation set. For the stereo, for the among all the methods which were tested, the classical methods like SIFT, surf, case, or freak, these are classical methods. Then we have a bunch of methods which have OpenCV SIFT, which is difference of Gaussian as a detector, and then learned patch descriptor, LTONet, HardNet, Geodesk, ContextDesc, SOSNet, and so on. And then we have end-to-end learned methods like R2D2, SuperPoint, ASLFeat, D2net, and so on. And it's interesting that Doc plus HardNet is the best at the time of the evaluation. Second, that actually lots of methods which are deployed and much more costly to evaluate, like again all these patch descriptors are not as that better than root SIFT, which is almost as good as KeyNet plus HardNet or GeoDesc or ContextDesc, despite being faster. One more thing is end-to-end methods are not good for the huge computational budget for 8K, but they're quite good for 2K, maybe because they were actually trained for on smaller images with smaller number of features. And as if you can see that for the 2K, it's actually the difference is much smaller than for 8K. And here are the numbers. We evaluated different transacts. What's interesting is that number of inliers, which you can see use as a kind of proxy metric, is not as good to predict your pose accuracy. For example, the Hessian is better plus SIFT in terms of inlier ratio, but worse as pose accuracy. For 2K methods, the state of the art is KeyNet, which was presented in the invited talk. And actually it kind of makes sense because it was trained on small images to have a best repeatability over a little number of key points, so kind of reasonable. And the SuperPoint and R2D2 are working not that well. For multi-view, you can see that difference is kind of much smaller than for stereoids, because when you have bundle adjustment, you can actually correct your pose when you have detected as much features as it's required to, and again see how good is root shift, which is again almost as good as best feature. And here is doc plus HardNet. Again, this is a table with both numbers, and actually you can see that the ordering is different for the things like ContextDesc. Now it's number 2, and probably because you're actually when for stereo you need to match actually whatever features just to be like precise. For the multi-view, it actually is better if you match the same features across all image pairs, because it's what is going to be survived in triangulation. For 2K, actually this is only kind of track where the learned detector is better than SIFT, and this is KeyNet, which again have a lot of handcrafted components inside. And here R2D2 works almost on par on it. So that is quite encouraging message for end-to-end learned methods. So it's probably need to be tuned up a bit, and then they become finally better than just this simple GOG. Now, additional finding: if images are upright for sure, and we make sure that they upright, and it is done by EXIF or by a photographer, it's better to don't detect orientation, but instead use upright features. And we have evaluated 2 things. First is you just remove duplicate key points, and it's actually a bit hurt performance. But if you then add features to get the same number of key points instead of those duplicated orientations, then you're 3 relative % better for all methods. So, and this is again kind of for free, because it's even less expensive because you don't need to detect orientation. And the same holds for multi-view. So the now question is, why did we pair the deep learned features like SOSNet, HardNet with DOG? Is it the best detector among the classical ones? And answer is yes. First, OpenCV SIFT is a bit worse than VLFit SIFT, but not as much. And the rest are not good. Hessian Laplace, Harris Laplace, MSCR, and so on. They're much worse. And what's interesting that it again, this is scene dependent, because on validation set, you can see that Hessian is better than SIFT, but on test set, which is like 5 times more scenes, actually SIFT is better than Hessian. Now I'm big fan of, at least, or was a big fan of affine features like Hessian affine by Krystian, or my own learned ASLFeat. So instead of just cropping the similarity covariant patch, you can learn or use some handcrafted estimation of local affine features, and it improves for better, for like bigger viewpoint changes. So does it worse the FAD or not? And answer is actually not for phototourism data. First is the difference is quite small comparing to the like just don't using this. And second, which is even worse, that it is not consistent. For example, for DOG, it's almost you have some improvement if you use affine, which is classical Baumberg affine thing, but it becomes worse if you use ASLFeat, and vice versa for Hessian. It is better with ASLFeat, but worse with, as Hessian affine is actually worse than plain Hessian. And again, here the results are kind of very, very similar for all the methods. Like Hessian or benefits the most, but if you compare it to just SIFT, it's almost the same as you do log affine or Hessian affine. And we don't have any explanation for this, but intuition is that you probably don't need this kind of invariance because you then matching more noisy features, and it hurts for your post precision. And this is qualitative comparison. So I encourage you to go to the website and actually check those images like in zoom in, and it's shows quite nice some problems of classical features as here or learned as in next slide. For example, Hessian features are super concentrated on edges and corners and not distributed enough. For methods like surf, you have a lot of things on background and so on. And for the learned features, this is my favorite part, because if you them in that, you can see that, for example, SuperPoint, it outputs super precise features on corners, but they are very, very sparse. Keynet is very similar to the actually SIFT features, but it's kind of more clean. R2D2 is like evenly distributed, but kind of still looks as not as precise. And D2Net, they actually think that they're detecting the same, it's trying to detect the same location among scales and locations, and have like a lot of noisy versions of the same feature. Like this is impression. So one could use these visualizations to maybe improve intuitions or methods. And here's a slide from the like 5 years ago work by CVPR publicity chair, and that's it is done with very different evaluation in very different setup than we did. It is with static cameras with different illumination and weather change and seasons change. And so successes are right here. Green local feature descriptor failed, and like you don't match these features. And blue is Keypoint detection failed. So, and the most of works just concentrate on this green area, and I guess that we kind of situated this already. And much more can be done on the local detector part. But the problem is that it's not clear how to train it, as we can see that end-to-end methods are still worse than simple blob detector like DOG. And some results from the competitions. So one thing is, despite that I said that it's probably better to improve the detectors, actually you can have improvement on tuning the descriptor. For example, here is HardNet and SOSNet as an trained on Liberty with this from the GitHub Authors implementation. And here what participants send us, and you can see that you can have quite a significant improvement just on tuning some parameters, how you work with data and so on for those descriptors. So just don't expect that off-the-shelf implementation is the best you can have. Regarding outlier rejection methods, here is baseline. It's actually not without outlier rejection methods. It's with just this low first to second nearest neighbor ratio. So this again not the best you can have. Add-along, which is very interesting method which will be presented here, is handcrafted one, and the rest are learned. And of course, the rock star of the current CVPR is SuperGlue, is improves so much better among the all other that no question who is the like true winner of this competition is. And here is the same for the multi-view. And what's interesting here, if you look here, is that for multi-view, the improvement is not that huge as for the stereo, just because having multiple images is actually easier to recover precise pose. And with this, I think, okay, I have a last slide that we have some progress in end-to-end learned features. We have new, I think, not published yet features disk here. And regarding R2D2 and like SuperPoint, you already seen the results. So at the end, that's it. If you have any questions, I would be happy to answer. And if not, I would pass to Eduard.
There is one question from Michal actually, which was, what do you think would be the best transact variant to try to implement on a GPU? Not for differentiability, just for speed.
Okay, I think that the best transact would be Maxac for this, because it's kind of, it has several loops inside which can be easily parallelizable. And moreover, it actually have some the methods for actually inner loop for local optimization is related least squares. Again, it's more optimizer friendly. So I would recommend Maxac++ for implementing on GPU.
Sounds good. I think we don't have any more questions, so we can go on with the slides. Can you unshare so I can? Yes, yes. Thank you. Let me see if I'm in the correct one. Hopefully I am. Okay, so let's briefly have a look at the results for this edition of the challenge. So the winners of the 2020 Image Matching Challenge are, we have two categories, 8,000 points and 2,000 points. For the 8,000 category, the winning entry is guided HardNet OANet by Chen Chen and colleagues from DT Global. And the runner-up is Luca Cavalli from ETH with colleagues from ETH and Chalmers Institute with Adalam revisiting handcrafted outlier detection. For the 2000 Keypoint category, the winner is SuperGlue, learning feature matching with graph neural networks by Paul-Edouard, Sarlin and colleagues from Magic Leap. And the runner-up is Disk, learning local features with policy gradient by Michał Tyszkiewicz. Have no idea how to pronounce that, I'm sorry. And the prizes are, we're going to have prizes for the winners and for the runner-ups, obviously with this being a special CVPR. We don't have anything that I can show you, but they are sponsored by Google. Thanks again for helping us out with that. And congratulations to everyone. Thank you for participating. I think from now on, we'll have the challenge participant talks, which come in this order, which is not the winning order or anything like that. The first one is Milan Pultar from CTU Prague. Let's see if he is around. Can you say something?
Yes, I'm here.
Okay, I'll unshare my screen.
Okay. I'll share my screen.
Yeah, you'll be able to do that.
Okay. Just, okay, can you?
Yes, we see your screen.
Okay. Fine, so I'll start. Right, so my name is, hi everyone, my name is Milan Pultar, and I just, okay. My name is Milan Pultar, I'm a master's student at the Czech Technical University in Prague, and I will present a part of my master thesis in which I focus on improving the HardNet local feature descriptor. In this talk, I will touch the architecture of the descriptor, the training datasets, the training setup, and the post-processing of the embeddings. In the image matching challenge, we placed fourth in this stereo track, and among the people who don't use custom matches, we will place the first. Therefore, we believe we have the best descriptor currently. Because we don't have access to the test set of the image matching workshop, we will evaluate the models in the following experiments on the validation set, and we will also use the H-patches benchmark and the AMOS patches benchmark. We introduced AMOS patches for evaluating the robustness of a descriptor to elimination changes. First, about the architecture, we experimented with these 5 variants of HardNet. The original HardNet is in the first column. In the name of the model, the ×2 denotes the models in which the number of channels are multiplied by 2. We wanted to find if increasing the width of the model improves performance. And we also wanted to find if increasing the depth of the model increases performance. Therefore, the models are at 8 and 9 contain 1 and 2 more convolutional layers. There are the results on the H-patches and IMW validation set are different. However, there is kind of a local maximum on IMW validation set for HardNet 8, and so we use this architecture in the solution. We also changed some of the convolutional layers to the residual blocks, so we tried these ResNet style architectures. Although these architectures outperform the original HardNet, none of these outperforms the HardNet 8 model. We also tried changing the final pooling in HardNet. Originally, there is a global pooling implemented by a convolutional layer. We tried to change this global pooling to a non-learned max pool or average pool and found that it either fails or doesn't or needs to burst performance. We also tried increasing the receptive field by using our stacked convolutional layer. This basically increases the depth of the model, and we found that it also doesn't improve the model. We also tried to change final pooling to local pooling, from global pooling to local pooling, in which the output descriptor is computed based on separate blocks in the input, similarly as is done in SIFT. This improves performance on the AMOS patches benchmark, which is a planar one, but it doesn't improve performance on the other 2 benchmarks. Regarding training datasets, we wanted to train on the provided training datasets in the image matching workshop. But when we extracted the patches based on the available key points, we found that some of the datasets are very large. Therefore, we used the following approach to select only a subset of the patches. First, we train HardNet for 1 epoch without propagating the gradients. And we save the observed loss for each batch. The distribution of the edges, which is the positive distance minus negative distance, is shown in the histogram. And in the histogram, you can see illustration, how we select the subsets of the patches. We can select the patches of the lowest, medium, or highest hardness. In the table, you can see that if we select patches of medium hardness, where the size of the subset is 10 times smaller than the full data set, we get better performance than if we train on the full model. Here is the evaluation of the reduction method. We can see that indeed, on the IMW validation set, the performance is similar or better if we train on only a subset of the full data set. On the H-patches full split, on the other hand, the curve is monotonic and the performance is always worse than if you train on the full data set. We compare the training data sets. We can see that there is a high variance regarding the performance on all the three benchmarks. We are not sure what is the true cause of this phenomenon, but nevertheless, we used this knowledge to select the data sets that we trained on for the submission. We also tried different data modalities. Here the experiment is on here we train the model on the AMOS patches dataset because we have RGB available, unlike in the case of UBC photo tool. D denotes the depth maps, which are estimated by a model trained on Mercator dataset. Plus in the table denotes concatenation of the two inputs. And in all cases, we trained the HardNet 8 model, but also in the last row, we prepended, we added a convolution layer with 1x1 convolution layer. And this is the only case where the performance is increased. We also wanted to decide on the input size of the patches. Originally, it is 32 times 32. One interesting thing to note here is that there is an opposite trend on the H-patches benchmark and on IMW validation set, meaning if the model improves on one of the benchmark, it often is worse on the other. We will also observe such behavior in the following experiments. We tried 3 different augmentations. Here, none denotes a simple downscale to the input patch size. This simple transformation gives the best result on the IMW validation set. The affine transformation gives the best result on the H-patches benchmark. And interestingly, if we add the anti-aliasing Gaussian blur to the affine transformation, we get a best result on the H-patches benchmark. There is also a related experiment. The H-patches data contain 3 subsets, easy, hard, and tough, which corresponds to the amount of augmentation applied to the data. And we also see that if we apply the least amount of augmentation, that we get the best result on the IMW validation set. We also wanted to decide on the batch size. The outcome of this experiment is basically the recommendation that you should during training, you should choose the batch size to be around 2,000 or more, depending on your specific training setup. We also performed an experiment on the margin. Here you can see that there is approximately a similar behavior on the 2 benchmarks. So I would say that it doesn't matter much what margin you choose if it is over 0.4. Now I will present the technique that we used to sample patches for a batch. The idea is to simulate the 2-view matching setup where the patches come from a single image pair. However, usually there are not enough key points per image, so we pick patches from only as few images as possible. We validated this idea on the AMOS patches dataset, and we can see in the figure that there is clearly an improvement if we sample from less views. That is number of cameras or number of images. This technique also leads to an improvement on the IMW validation set, and therefore we used it to train the submitted model. I also present, we also post-processed the embeddings from our model. We use PCA, which is fitted on the embeddings from Liberty dataset, and we embed it to the model. So we can see on the figure on the right that if we decrease the dimensionality of the outputs, we get better result on the IMW validation set. However, on the H-patches benchmark, there is a small decrease in performance. Now I will compare our model to other descriptors. Besides the model that we submitted to the image matching challenge, we have also trained a universal descriptor which improves results on all benchmarks, and we would be able to adjust to any to other use cases, mainly by using different training data. Here is the description of our submission. We use the Baker HardNet 8 architecture and use PCA to reduce the dimensionality of the embeddings. We train on 3 datasets and use a bigger bit size and a margin equal to 0.5. We also use the presented technique to sample patches for a batch. The submitted model and also the universal descriptor are publicly available. This is the conclusion which corresponds to the previous slide. Thank you for your attention. And if you have any questions, feel free to ask.
Thank you so much, Milan. And yeah, there is a couple of questions in the chat. So Jatantaki is asking if you have tried training without flips. Like, unlike rotation, flips do not occur naturally, and maybe it's not a good idea to use them. Do you have any experience doing that?
No, actually, we have not performed an experiment that we keep the current setting and turn off the flip and rotation on.
Mm-hmm. So
okay, I can answer this. So the flips are done for the both patches simultaneously, and this is kind of also this 90 degrees rotation, which is the same for the both patches, and is done for SASNet and all other stuff, which is helps a lot for the H patches, but we haven't checked if it helps for this photo-tourism dataset.
Okay. I also have another question, actually. Well, this is my personal question. So any ideas or guesses on why using certain data sets are better and some are actually harmful?
No, this is, we have spent a lot of time thinking about this, and we don't have any clear conclusions yet.
It might actually be the holy grail.
Yeah, we would really like to answer such question, and we'll probably do some research on that. Yeah.
All right, so I would like to then thank Milan again. Claps. And I think the next speaker in line we have is actually as Dmytro said, rock star in the CVPR probably.
Okay,
so
I will stop sharing.
Yes, please do. And I would like to invite Paul-Edouard to present SuperGlue. And without further ado, the stage is yours.
Hello, thank you for the intro. Let me share my screen. All right, you should see it now. Cool. Yeah, thanks to the organizers for inviting me to talk about SuperGlue. So let's dive in. I'm Paul-Edouard Sarlin. I am a PhD student at ETH Zurich, supervised by Prof. Mark Polyphase, and this is our winning entry to the image matching challenge based on our paper SuperGlue: Learning Feature Matching with Graph Neural Networks. And this work was carried out when I was at Magic Leap during my master's thesis in collaboration with Daniel Detone, Tomasz Maliziewicz, and Andrew Rabinovich. So yeah, so we got the first place with SuperGlue in this challenge for the category of restricted key points, so fewer than 2,000 key points. And we did that with SuperGlue, which is a deep neural network that performs feature matching. So in this talk, I'll first give an overview of SuperGlue without going too much into details, since that was presented at several occasions this week, sponsor sessions in other workshops. And I'll focus on the specificities of this challenge and the little improvements that we added that improved our ranking further. And finally, some results and some analysis and thoughts. So yeah, SuperGlue is a graph neural network, so it's a combination of a graph neural network and an optimal transport layer, and we call it the middle end since it estimates matches between local features in two images, and at the same time it rejects unmatched points, and it can successfully match image pairs with extreme baseline in near real time. As you can see here on some indoor scene. And that results in state-of-the-art pose estimation with both classical and learned features for both indoor and outdoor environments. So maybe, so we've seen this minimal matching pipeline, which turns out to be the one that is evaluated in that challenge. So we've talked about detectors and descriptors, classical or learned, and then very often these descriptors are matched with the nearest neighbor in the descriptor space, and as it's often naive and prone to failure if the descriptors are imperfect. And as we've seen also in the results of a benchmark, it's very important to have methods to filter out outliers, and these can be heuristics like the ratio test or deep networks that classify elements of a set. And finally, we're estimating a relative pose with something like RANSAC. And in contrast to all of these, SuperGlue is a bit special because it performs at the same time context aggregation, matching, and filtering in some kind of unified architecture that is trained end-to-end. And the ability to leverage global context is very important in situations where we have a lot of self-similarities or little texture, such as in this checkerboard example, where without that much context, which SuperGlue has, it's very difficult to match all these corners that look all the same. So SuperGlue takes as input two sets of local features, and as Dmytro mentioned earlier, it really takes a very large set of inputs. So as features, we mean both visual descriptors and key point positions, in contrast to its other matchers or outlier filters. And SuperGlue outputs a partial assignment matrix from which we can extract matches and also know which points are not matchable. So SuperGlue is composed of two blocks. The first is a graph neural network that processes the appearances, the position with powerful attention mechanisms. And this encodes contextual cues, priors into the deep features, and this block kind of reasons about the underlying 3D scene. And then the deep features define the cost of a partial assignment problem, which we solve in a differentiable manner. And that produces this partial assignment, which in the end enforces some domain-specific constraints. So we train SuperGlue on pairs of images that have depth maps and relative poses, and that are obtained from structure from motion. So we trained the outdoor model on the megadepth dataset. And so from these depth maps and relative poses, we can compute ground truth matches, and we can also know which points are really not matchable. And these are these red points. And these provides direct supervision to the partial assignment matrix, and everything is trained end to end. So using these quantities, SuperGlue can in some way learn the concept of visibility and understand which parts of the image are actually not matchable. So we evaluate on outdoor data sets, very similar to the ones used in this challenge. And we see that SuperGlue gives very reliable matches, a lot of correct matches, and very few mismatches. And it really works much better than both heuristics and classical matchers, and also some of the recent deep matchers. So in the paper, we have some evaluation on indoor data sets and outdoor data sets. We apply SuperGlue to both SIFT in blue and SuperPoint in red, and we see some very large improvements in all cases. So regarding this challenge, we go in a few steps. We extract features using SuperPoint, and because these were our best results. And then we match these features using SuperGlue, and we use Degensac to clean up some of the most noisy matches. But here Rensac does much less work than with classical matchers. So then we tune some of our hyperparameters on the validation sets. It's mostly Rensac. There's not much to tune elsewhere. And then we submit, and we wait for the results. So we can actually look further on at the challenge rules. So we'll talk about the number of key points with a budget of 2,000 key points. Yeah, that's okay. We've done all our evaluation on that, and SuperPoint doesn't produce so many key points, so actually that's perfect. And then we look further, and we see that it's actually limited to 128 dimensional descriptors. It turns out that SuperPoint is 256 dimensional. So would that actually disqualify SuperGlue? Well, yes, that means that SuperGlue will not be able to participate in the challenge. So we had to use some additional improvements. And the first one that solved these constraints is to use an autoencoder to map 256 dimensional SuperPoint features to 128 dimension. Supervised with a L2 loss, that's very simple. We can change the dimension and produce even smaller descriptors. And the nice thing is that there's no loss of accuracy. So there's exactly the same performance between the 256 and the 128 dimensional descriptors, and reducing to 32 dimensions gives a loss of 1% of pose MAA or AUC. So that's very easy, and that allows to actually be eligible for the competition. But then when we actually look at some images further, we realize that there's a lot of detections in the sky. And that is not super nice, given that we have a limited budget of 2,000 key points. That means that we're actually wasting most of our budget on points that will not be useful for the pose estimation. And that happens for a lot of images on a lot of sequences. And that happens on also especially on scenes where there was a scene to match is very small, so we actually need a lot of key points to be precise. And also we waste some key points on the people. So the second step to mitigate that is to run semantic segmentation to remove the key points that are in the sky and on the people. So we run a classic segmentation network. The details are on the challenge webpage. And that's we can remove all the key points that fall on the mask. They are in red. And that way we can actually detect more key points on areas that are relevant, so more areas on the areas that can be matched. And that makes a significant difference at a limited budget of 2,000 key points, of course. So now the pipeline looks like this. For the image, we also compute a semantic segmentation, and we use it to filter the key points at the end of SuperPoint. So we can actually look further at the heat map that are produced by the detector of SuperPoint. And it turns out that now the bottleneck is the actual key points, because we have really good matcher. Rensac works pretty well. And we're not really wasting key points, but still the performance is not really the maximum achievable, and we think that's because the key points are somehow noisy. And then we recall the training procedure of SuperPoint, and there is this step called homographic adaptation, where for a given image we can sample a lot of different homographies, and we can warp this image with each of them, apply SuperPoint on each of them, and then warp back the heat map, the key point responses, and obtain some kind of aggregated heat map that reflects the heat map that would be seen from many different viewpoints. And that's the point superset, the SuperPoint. So here, instead of just using SuperPoint, the vanilla SuperPoint that is trained, we actually apply this process at test time, where for test image, we actually run this process and we see much better heat maps that are all nicely refined here and there. And if we zoom here at this point, we see a nice blob shape. And on that, we can, for example, apply some subpixel refinement like the soft argmax and really get very precise key points that are much better repeatable than the original SuperPoint. And that's the key point that we can extract. Some nice grids, some nice corners that are very well localized, even from different viewpoints. So now the pipeline looks like this. It's a bit more expensive since you have to run SuperPoint 10, 20, or 50 times, but at least we have stronger key points. So looking at the results, this was a baseline with the improvement number 1, the autoencoder. The competitors are in green, and the SuperPoint with the nearest neighbor matcher is in blue. So let's say that SuperGlue gives a pretty big boost compared to just the simple heuristics that were used before on SuperPoint. So adding the masking of a key point improves further. This is the average on the stereo and the multi-view tasks, but on some sequences that helps a lot. And then using the adaptation improves the result further. And to give you an idea, these are all the competitors for the track that has restricted key points, 2000 key points, and this is the best method for the 8,000 key points track. So we're actually getting very close to it, much closer than all the other competitors that also run on 2000 key points, which shows that with SuperGlue, we can really match all the key points available, and we actually probably don't need much more to reach the same accuracy. So we can visualize, we can look at some of the results. Here, some matches, for example, in green. Okay, that looks reasonable. We can also look at the key points that are reconstructed by SFM, by CallMap in blue, and we see that SuperGlue can really reconstruct all the key points that appear in self-similarities, these styles here, or at the top, which is actually something that requires a lot of context. Otherwise, you can get a lot of these matches wrong. So this makes a big difference, especially on that sequence where SuperGlue is much further ahead of all the other methods, because it can use so much context to match all of these details that are actually very important for the accuracy of a post, because they average out the noise in the key points. So that's pretty much it. If you have some questions, feel free to reach out by email or on Twitter. You can find our paper, the code, the demo, the slides, and some links to talks I gave at some workshops at CVPR this week on our website. And with this, I am happy to take some of your questions.
All right. Thank you so much for the great talk. While we wait for some questions, I guess I can ask a quick question. Mm-hmm. So my question is, how important are the visual features? Have you tried removing the descriptors and just using the coordinates?
So it's not something we've tried. It's something we've been thinking of doing at some point. I believe that they're somehow important to guide the matching in some ways. I believe they're important to somehow guide the matching to roughly align. But I think that in some situations they're not necessarily required because there are a lot of patterns in the key points. And exactly. Especially if you have a key point that has a nice repeatability, then there is actually a lot of information in the key points. And I think that SuperGlue really leverages a big part of that information, especially in situations where the descriptors are very weak. And these for SuperPoint, that happens when you have very large scale changes, or when you have very extreme, I think, illumination changes. So these things can happen, and I think that's one of the ingredients that makes SuperGlue very powerful. And we see it here where with 32-dimensional, of course, the descriptors are not as good, but they're still good enough for SuperGlue to match with still very high accuracy.
I see. So actually a question from one of the authors. So what do you think would be the next thing to improve SuperGlue?
That's a good question. Well, we can go back to the pipeline and we can see what hasn't been incorporated into SuperGlue yet. So in a sense, SuperGlue can improve the descriptors a lot, so we can probably not improve much further on that. It can do the matching and it can do the filtering. One thing that SuperGlue doesn't do yet is estimating a pose and detecting key points. Well, the key points, maybe we can leave that to SuperPoint, and we have some tricks to improve that. So maybe we could have some pose estimation with SuperGlue that could be maybe incorporated in the training.
Wouldn't your matching results already be an implicit representation of the pose, actually?
There are in some ways. The problem is that we still resort to some heuristics for the training and the labeling, basically, of its correspondences. And we can only accept the match if it's within a few pixels threshold. So that's why we still need BrainStack for now to actually keep really the most precise matches at test time. But ideally, we would like to train with these constraints so that SuperGlue is trained just to produce an accurate pose. So that's something we don't have yet.
So, well, actually, there's one more question. I think I'll move on to the next one after that. So, what's the runtime of with SuperPoint, homographic adaptation, and everything that you did on top for the challenge?
Mm-hmm, mm-hmm. So it's more expensive for sure, because here we run, to be safe, we run the adaptation with 50 iterations. So that means we actually run 50 times more feature detection, which is of course more expensive. But I believe that all of these could actually be distilled back into SuperPoint. Because the SuperPoint that we had was trained with a cross entropy just to maximize the score of 1 pixel, but we could actually just distill that augmentation into SuperPoint. That's possible, and maybe we would have a network that has better heat maps. The semantic segmentation is also expensive, surely, but I also believe that this also could actually be learned by SuperPoint itself. So we use these tricks because SuperPoint was trained on homographies. And instead of retraining SuperPoint, we use information we have available elsewhere. But a SuperPoint trained with this extra information on SFM data would actually also incorporate all of these priors ideally and have just better key points by itself without these tricks.
I see. So since we have limited time, there are much more questions in the chat, I think.
I'll answer them on the chat then.
Thank you so much. So thank you, Paul. I will, next speaker we have is Shuhei. But because it's like 4 a.m. in their time, they sent us a video that I will actually play instead. And I pray to God that I click on the right buttons to get the sound working as well. So bear with me.
Hello, everyone. This is Zhiqing from Hong Kong University of Science.
I need to stop first and then. Okay, my laptop is being fried, but hopefully it doesn't get fried too much.
I can try it on my end if you want.
Give me 5 seconds. Got it. So share screen, share computer sound.
Today, I will, together with Jiahui Zhang from Tsinghua University, to present our method, ContextDesc or ASLFeat plus OANet for this workshop competition challenge. For local feature extraction, we first resort to ContextDesc, which is a learned local feature descriptor we have presented last year, and have also used it to participate in the previous workshop challenge. The ContextDesc model is trained on GL3D dataset, and the exact same DOG key points as used by HardNet or SOSNet are selected to perform the feature extraction. We have tuned the descriptor to boost the performance on this benchmarking dataset, including that we have omitted the key point orientation during the inference time. Also, we retrain the ContextDesc model with less rotation perturbation during training, which is the same scheme as used by HardNet. So the reason to do those tweakings is that this benchmarking dataset is exhibited only in small rotational changes. So it is not necessary to have those descriptors invariant to arbitrary rotation. This year, we further bring a new feature, ASLFeat, to participate in the competition. ASLFeat jointly learns local feature detections and local feature descriptions. We use its original model, which is trained on GL3D dataset, and select up to 8,000 key points and perform multi-scale detections. We have observed that it is of great importance to increase the scale invariance with multi-scale inference on this benchmarking dataset. And we will discuss the results later, but it seems that the advantage of learned key points is more obvious in terms of large elimination change. You can check out the results from the real localization workshop. Unfortunately, ASLFeat does not deliver consistent improvements upon ContextDesc on this benchmarking dataset. Even though in the original ASLFeat paper, it is shown that a learned key point can be a safe replacement of a handcrafted key point. Eventually, it seems that there still exists some performance gap regarding large perspective change, which needs more effort to mitigate. Actually, the performance gap becomes even more notable when compared with the best patch-based method. It would be interesting to find out what leads to such performance gap. Is it because the patch-based feature extraction is more suitable than dense feature extraction for local feature learning? Or the DOG key points are better localized than learned key points? Or perhaps an explicit shape estimation of scale or rotation parameters is the key to acquire stronger perspective invariance. So those are still some open questions that need to be resolved in the future. To further boost the performance, we equip OANet, which learns to reject outlier matches for feature matching. The OANet model is trained on WebCC dataset, and we discard those matches whose confidence scores predicted from the network are lower than some threshold. The OANet has delivered consistent improvements on both ContextDesc and ASLFeat, and this year we have upgraded OANet to OANet v2, which will be introduced later. Next, I will briefly go through the methodology of ASLFeat. In this paper, first, we address the importance of estimating accurate local shape of key points for improving the geometric invariance. More specifically, we resort to deformable convolutional networks to densely predict and apply local shape transformation. Furthermore, we compare different parameterization of deformation and study what deformation is useful for learning invariant features. Next, we address the importance of key point localization accuracy for solving the geometry. And more specifically, we adopt the hypercolumn representation and perform a multi-level detection to recover the low-level geometric structures and restore the spatial resolution accuracy. Meanwhile, we compare different network designs to explore the efficient way for feature fusion. We base our methods on D2Net framework and apply aforementioned modifications, namely deformable convolutional networks and multi-level detection. We optimize the implementation with other minor changes such as a pickiness measurement and an adaptation of advanced loss formulation. We thoroughly do ablation studies and extensively carry out experiments on image matching tasks. Structure for motion, image retrieval, view localization, and dense reconstruction tasks. The empirical results show that our methods have delivered remarkable improvements upon the state of the art. Thank you for your attention.
Hi, this is Jiahui from Tsinghua University. I will give a brief introduction to OANet, our learning-based outlier rejection method presented in last year's ICCV, and I will introduce an improved version of OANet used in this challenge. Here we focus on the two-view geometry estimation problem, which is, given a pair of images, we estimate the essential or fundamental matrix. We construct putative matches by using SIFT or other learned local features. Then, to obtain accurate relative post-estimation results, we have to find these outliers. In this paper, we'd like to use a network to distinguish the outliers and inliers. One of the challenge is how to capture the local context for the putative matches. This is non-trivial because they are sparse and unordered, and our solution is using learned clusters to capture the local context. Here is an overview of our architecture. The input of the network is image coordinates of putative matches, and the output are inline probabilities and EF matrix. We use a unit-style architecture. The core of the network is the differentiable pooling and unpooling operation. The differentiable pooling layer clusters input nodes to a coarser representation by learning a soft assign matrix. Matches fall into the same cluster are learned neighbors. The network can capture local context by this clustering process. The differentiable unpooling layer can be simply seen as a transposed version of differentiable pooling layer. Besides, as shown in the right figure, we show that these clusters obtained by differentiable pooling layer are in canonical order, which means we can capture the relation between these clusters using more powerful operations, such as fully connection layer between clusters. These two operations both bring notable improvements. We extensively conduct experiments on several benchmarks. Our method can outperform both previous state-of-the-art RANSAC variants and learning-based methods. As shown in the figure below, it works best when using RANSAC variants as post-processing in WebCC, but can achieve better results when not using post-processing in Sens3D. This demonstrates that our method has the potential to be not only an outlier rejection method, but also a robust estimator. Besides, we also test the network's generalization ability on 4 different datasets. The model is trained on GL3D, a much larger and diverse dataset. We test it on 2M indoor scenes, Kitty, Tank and Temples, and community photo collection. Our method generalize well and outperform both handcrafted methods, such as GMS and learning-based methods in these benchmarks. Besides, our method is quite practical. It takes 20 milliseconds on GPU or 100 milliseconds on CPU. Here we introduce the OANet v2, which equals to OANet v1 plus stacked August network. OANet v2 contains a set of August modules, which repeatedly downsamples and upsamples feature maps. Each August module is composed of 1 differentiable pooling layer, 1 special correlation layer, and 1 differentiable unpooling layer introduced before. To reduce the computation and overfitting, we propose a bottleneck special correlation layer, which first downsamples the clusters and then upsamples clusters. Without increasing too much computation, OANet v2 can significantly improve the performance. Above is our evaluation on YFCC for essential matrix estimation using SIFT. It can give an improvement of 11 points when not using RANSAC post-processing. Below is the result from CVPR RANSAC tutorial held several days ago. OANet v2 plus MaxEC++ achieves the best result among several recent works, including 2 CVPR papers this year for both fundamental and essential matrix estimation. Here are the results in this challenge. We trained 2 models for upright context descriptor and ASLFeat v2, and then used DigenSec as post-processing. Models are trained on the YFCC dataset using 4,000 points and tested with 8,000 points. These models are both effective, especially in the multi-view track. For upright context descriptor, we found it works best when applying mutual check first and then OANet v2. But for ASLFeat, it works best when using only OANet v2. Thanks for your attention. You can check out our code on GitHub. Feel free to contact us if you have any questions.
Okay, so unfortunately, we don't have the authors presenting in person. But that's the fun of having these things virtually, I guess. So we'll move on to the next speaker, which is Tony. And I think, yes, he is in the room. So without further ado, Tony is from Imperial College, London, and he'll give us a talk about his submission.
Hi, thank you for the introduction. Just let me try to share my screen here. Is that working?
Perfect.
Yeah, great. Hi, I'm Tony. Today with me is Axel, Barroso-Laguna, and Yurin Tin, and we're from Match Lab at Imperial College London, led by Krystian Mikolajczyk. For the guys who didn't attend earlier, he gave a speech earlier at this very same workshop. All right. So here you can see today I'll be talking about our entry to the challenge, HighKey.net. So this is our overall pipeline. So the main novelty is basically we build on our new Keypoint detector, Keypoint.net, and our very new descriptor as well, HighNet. So that's where you get the HighKey.net from in the naming. So our focus is on improving these 2 separate parts, and we like to argue for why separate Keypoint detector and descriptor are still quite competitive in these sort of tasks for image image matching. So we're using basically the built-in nearest neighbor matches and RANSACs. So the talk will be broken down into 3 parts. So Axel will first talk about how he uses different tricks to improve the Keypoint detection with a limited budget, of course. And then Yurin will be going through the new descriptor HighNet, and Lars will be wrapping up with some discussion on the challenge results and some visual examples as well. So I'll hand over to you, Axel.
Hi, thank you, Tony. Hi, everyone. I'm Axel Barroso-Laguna. Can you go back to the segmentation, please?
Sorry.
First of all, let's see our semantic segmentation. So the idea was pretty simple. We use a pre-trained network from Deep Lab v2 to define which areas of the image are important. Therefore, we will segment those images such as we can later on split them into desired and undesired areas. We define unwanted classes such as clouds, pavement, sky, grass, as in the example above. And on the other hand, we also define the desired classes such as columns, buildings, statues, etc. But as we know, semantic segmentation is not perfect. And we define some rules to avoid using masks when they are incorrect. The idea is that we define a threshold for the positive and the negative mask. If we don't reach the number of pixels within any of the masks, we will discard them and use the full image. That prevents us from misusing semantic segmentation when we are dealing with scenes that don't contain buildings or that the building wasn't correctly detected. For instance, we observed that when dealing with human face structures, our semantic segmentation wasn't able to select correctly the interest areas. In the bottom, you can see an example of keypoint score filtering through a segmentation mask, where those keypoints belonging to the building are kept, meanwhile those from the glass are discarded. We use our recently developed KeypointNet as our detector. KeypointNet was presented last year at ICCB. And as Krystian mentioned earlier, the main novelty of KeypointNet relies on the combination of handcrafted and learned features, and in the learning scheme. As also was presented in the local feature Mondays tutorial, many classical methods still show top performance. KeypointNet architecture was built to combine successfully classical methods and the latest deep learning approaches. Therefore, we designed our set of handcrafted features borrowing the ideas from classical Harris and Hessian corner detectors, which we know that work well and are reliable. In addition, we extend our network to multi-scale detection by feeding a scale parameter within the architecture, trying to mimic the boost of classical multi-scale detectors. This set of handcraft features are then the input to the learnable blocks. In the learning, we propose to extend the covariant loss function presented by Carol Lenk and Andrea Bedaldi to a multi-scale paradigm. By adding the different scale during training, we allow the network to learn a ranking of the key points, not only looking locally, which is the most prominent, but also identifying globally, which is the most discriminative. As you can see in the right part of the slide, as we add scale levels on the loss function, we move from cluster of key point detections to a more spread out detection score over the image. We leave you the archive link for further reference. Here, we show you some repeatability result on benchmark. We use the full images provided in H patches, which is commonly known as H sequences. Therefore, in the table, we can see results when using the top 1,000 points detections in each image. We see that KeypointNet gets the best results over all previous methods, followed by SuperPoint and HDDNet, which uses KeypointNet backbone architecture, but includes a loss term that improves the matching score of the detection, still providing high repeatability scores. We see how competitive those methods still are, ranking above the latest ASLFeat and R22 methods. Note also that KeypointNet and SuperPoint are trained both on synthetic images, and results could be potentially boosted with real data. And that will be all for feature extraction. I leave you now with Euron. Thank you.
Hi, thanks, Tony and Axel. And my name is Euron, and now I'm going to briefly introduce our new discriminator HardNet. Well, HardNet achieves state-of-the-art patch matching performance through the standard triple loss with a hybrid similarity measure. And its design is based on our observation of how different similarity measures generate the gradients. And specifically, we look into the two widely used similarity measure in the product and L2 distance, and investigate how they generate gradients for L2 normalized and unnormalized discriminators. And first, we observe that optimizing a pair of L2 normalized discriminators is equivalent to optimize only the angle between them, while optimizing unnormalized ones will also affect their magnitudes. However, discriminator magnitudes are not directly related to the matching performance, and blindly modifying them may distract the training. So we propose a regularization term that can provide beneficial gradients by requiring matching discriminators to have a similar L2 norms before normalization. And then, after reviewing the distribution of discriminator space, we found that both the inner product and the L2 distance are biased towards either positive or negative samples. Since intuitively, the strength of the gradient should be adaptive to the hardness of the training sample. That is to say, hard samples should get more optimization, while easy ones get less. Therefore, we propose a new hybrid similarity measure combining the inner product and L2 distance to alleviate this problem. And finally, The loss function is a hybrid similarity-based triplet loss with a regularization term. And also we use the hard negative mining strategy proposed in HardNet, which has been proven to be very effective. And besides the loss function, HiNet shares a similar architecture with the previous method like AutoNet, HardNet, SourceNet. And the major difference is that HiNet employs the newly proposed filter response normalization instead of the batch normalization, which enables it to auto-normalize not only the output discriminators, but also the intermediate feature maps. And HiNet takes 32 by 32 grayscale patches as input and outputs 128 dimensional discriminators. And for the challenge, HiNet is trained on the Liberty subset from the UBC data side. And for more details of HiNet, please refer to our archive link and our GitHub project page. Well done. We show some, Tony, next slide. Yeah. So we show some evaluation results of high Keypoint night on H sequence, where we can see that it gives the best overall performance, surpassing all joint methods, including the recent ones like R2D2 and ASLFeat in terms of both matching score and repeatability. And then we further test HiNet on the structure from motion task, and which is shown in next slide. Yep, and we show that when using the classic DOG detector, HiNet significantly surpass previous state-of-the-art local discriminators like HardNet and SourceNet, and by registering more images and producing more reconstructed sparse and dense points. And moreover, when replacing the DOG detector with KeyNight or high Keypoint night, can get further improved performance. And thanks, that's for the HiNet part. And next, Tony will continue to present our results in the challenge. Thank you.
All right, thank you, Alex and Jeroen. I hope you have more understanding on Keypoint.net and HiNet separately. So now that we've looked into the performance and benchmarks for the detector and the descriptor, let's now see how high Keypoint.net compares with others in the actual challenge itself. So in the top table here, we like to compare our methods with the other top methods that only use the built-in matches, which has shown like the custom matching. This I'll talk a bit more. It's quite important, and yeah, we can see that the ranking without custom matches. We can see robustness of using high Keypoint nets, the two separate parts. It still gives pretty decent performance. In the bottom here, like everyone knows about SuperGlue now. You can see like how important just having a custom matcher is on top of a detector and descriptor without it. So yeah, we can see like there's a huge potential of like improving both the detection and descriptor part and the custom matcher part for the pose accuracy in image matching. So this next slide here, we like to compare, argue for, separate independent detector and descriptor is still quite competitive compared to all these other joint detector descriptor methods. You can see from the ranking and the actual pose estimation here. So yeah, even though our things are not jointly optimized, it still gives quite competitive performance on pose accuracy. At the bottom here, we just like to reinstate that Keypoint.net is very robust in the keypoint repeatability part, which probably helps contribute to our decent performance on the challenge. Well, this slide I'm going to show like some visualization, as just like Paul-Edouard has showed earlier with his presentation on SuperGlue, how important it is to use the semantic mask, especially for limited keypoint budget. So left-hand side here, we see all these red points being detected by our detector, which is quite irrelevant for the multi-theory reconstruction using CoMap. And you can see it's the same for the bottom image here. So with a limited budget of key points, you can imagine like detecting all these points would be quite wasteful. So yeah, using the semantic mask that Axel introduced earlier, we can see that we have a lot more densely populated points in the parts that actually contribute to the 3D model. Same goes for the bottom image here. So lastly, we'd like to show an ablation study of how we actually got into our final entry. So our first trial was just using a naive Keypoint net and our older descriptors. And then we try adding the multi-scale pyramid, as Axel have presented earlier, and we can show that it actually helps a lot in the pose estimation. Then we discovered that for 2K at least, the GenSAC is quite a bit better than MaxSAC, which is, I think, probably confirmed by Dmytro in his in the benchmark paper as well. Yeah, so semantic mask, you guys have seen the visualization as well, so it's pretty clear why semantic mask helps. And lastly, we have our new finalized descriptor HardNet as well, and that's what's bringing us to our final submission. Yeah, so in conclusion, our detector Keypoint net gives the state-of-the-art result in the Keypoint measure repeatability of keypoints, even at very low reproduction error thresholds. Our new descriptor HardNet gives the state-of-the-art result in its own kind of benchmark. So, like, we argue for that independent keypoint detector and descriptors can still compete quite robustly with these jointly trained methods, and we look forward to seeing what the potential could be when we add like a custom matching sort of method like SuperGlue as presented. So that's all. Time for questions. Should I stop sharing my screen?
Yeah, so thank you for the interesting talk. We just noticed that we're running quite a bit late on time right now. So if there are no particular questions in the chat, we will move on to the next talk that we have. And we would like to direct all. Yes, and clap. Yes. And clap, and we would like to redirect all the questions to chat or directly contact Tony, Axel, and Yurin. Thank you again for nice talk.
Cheers.
Okay, so our next two talks actually would be in video. So I'll be again trying to present this video for them. So give me 1 second just to share my screen. And there we go.
Hi everyone, my name is Chen Sheng, and our team is mainly from Map Vision Group, Dmytro Mishkin, Peking University, and Xiamen University. Today, we are pleased to share our method in image matching workshop 2020. Our topic is better data, better result. The difficulty in image matching is due to partial occlusions, image deformations, and viewpoint or illumination changes that may occur across different images. We propose our solution to the image matching problem compromise 3 operations. The first is repeatable key point detection. The second is reliable descriptors extractor, and the third is powerful outlier prefilter. We adopted SIFT to detect key points, HardNet to extract descriptors, and the guided matching or the OANet to prefilter outliers. The pipeline composed of these methods has achieved excellent results in the competition track 1. As we all know, deep learning is data-driven. In experiments, we found that the better data resulted better model. So we did a lot of work to improve the dataset. In the beginning, let's talk from key point detection. Seen as common practice in leaderboard space lab, we adopted OpenCV implemented SIFT with a fixed orientation to filter out duplicate orientations, and a low detection threshold to generate up to 8,000 points. In the experiments, we found that the more SIFT features points, the better. In terms of discriminative extraction, we made two improvements to HardNet. The first was to adopt a quadratic loss form. The second was to construct a clean patch dataset with less redundant data and noise label. HardNet is the state-of-the-art data-driven descriptor extractor, where a simple 7-layer convolutional neural network is applied to each 32 multiplexed 2 patch so as to extract its descriptor. Inspired by ASLFeat, we employed quadratic hinge triplet loss instead of the conventional hinge triplet loss. The proposed loss maximizes the distance between the positive and the closest negative example in the batch. Compared with conventional hinge triplet loss, quadratic hinge triplet loss with the gradients with respect to the parameter of the network by the magnitude of the loss. This means that the larger d negative minus d positive is, the smaller the gradients are. What's more, in the experiments we found that it makes the model more stable. The quadratic hinge triplet loss is more sensitive to outliers in the dataset. For this reason, we need to construct a dataset with less noise label. We use the aforementioned SIFT method to extract patches from photo-2-array training scenes. We triangulated features with known poses from given sparse modules by using point triangulator from COMAP. After constructing the 3D models, we discard 25% images with the least 3D points and discard 3D points whose track length is less than 5 to reduce noise labels. In order to accelerate the HardNet training converge progress, we removed redundant positive data by sampling only 5 patches from those track lengths more than 5. We do the sampling operation 10 times for each 3D point and keep the group with the lowest mean normalized cross correlation. In summary, we construct a dataset for HardNet with less noise and redundant data from the photo-2-array training scenes. For each scene in the training set, we trained HardNet with quadratic hinge triplet loss. It boosted the result under the same ratio test parameters as shown in the table below. In our lab prefilter module, we tried the guiding matching and the OANet. The guiding matching and the OANet module can be used separately or in combination. In guiding matching, interest point correspondences are determined using estimate fundamental metric to define a search strip about the epipolar length. Since the search area is restricted, a weak similarity threshold can be employed. Generally speaking, inadequate correspondences may lead to inaccurate post-estimation. For the image pairs with the number of correspondences less than 100, we propose dynamic guided matching to increase the number of correspondences. Different from traditional guided matching, the dynamic threshold is applied on the Sampson approximation constraint according to the number of correspondences of an image pair. We argue that less number of correspondences requires greater threshold. The dynamic threshold is set by this formula, where initial threshold is 6 and n is the number of original correspondences of an image pair. The OANet infers the probabilities of correspondences being in layers and regresses the relative pose encoded by the essential metric. In our experiments, we found that the learning of classification on correspondences played a major role, so the correctness of the correspondences greatly affects the ability of the model. The inlier-outlier labels for correspondences are derived from epipolar geometry using the Sampson approximation, and a threshold of 10,000 is used to determine valid correspondences. We argue that a byte data comes from a street label. Consequently, we constrain the Sampson approximation from 10,000 to millions. Furthermore, we calculate the reprojection error of 3D points and mark the correspondences with reprojection error greater than 10 pixels as negative samples. Two constraints on labels above greatly improve the correctness of Lagrange truths. Here is our aggregation study on benchmark validation set. As shown in the table, modules all took significant roles in our result. Here is our result on leaderboard. In 624, we first used the OANet then guiding matching. In 6590, the guiding matching was adopted only. That's all. Thank you.
Okay, yes, so I would really love to have these speakers on board because I had a lot of questions for them because this is the winning entry after all. I'll move on to our next speaker on the list. Yes, we should have planned this a little bit better. I wish there was no time zone difference in the world. I mean, the Earth is flat after all, right? So yes, sorry, that was a bad joke. I'll go and play the next presentation that we have.
Hello, everyone. I'm Yuan. I'm very glad to introduce our missions to the IMW 2020 challenge.
And there you go. Okay, so our next speakers are from University of Hong Kong, and without further ado, I will play their video.
Hello, everyone. I'm Yuan. I'm very glad to introduce our submissions to the IMW 2020 challenge. Here is a brief summary of our submissions. Our pipeline consists of 5 components. We use the KeyNet or CVPR20 to detect key points and extract gift descriptors on these key points. Then, nearest neighborhood matcher is used to produce a set of initial correspondences. These initial correspondences are filtered by the GMC net, and the fundamental matrix is estimated by the DGensec. Our results are shown in the table below, and in this talk, we mainly focus on the gift descriptor and the GMC net filter. First, let me introduce the gift descriptor. In gift, we want to learn descriptors that are invariant to scaling and rotation without relying on transformation-covariant detectors. We draw some inspiration from equivalent feature extraction. The definition of equivalence is illustrated by the following figure. Given the input data I and the feature extractor F, the equivalence is shown by the equation here. It means if I is transformed by a known TG, then the output feature is also transformed by a known TG prime correspondingly. In our cases, we first warp the input image with a set of predefined transformations, then we extract feature vector from these warped images by the same CNN. So every image here corresponds to a feature vector here. If the input image is downsampled and rotated, we apply the same warping and CNN on the transformed image to get a feature map like this. We can see that there will be one-to-one correspondences between these two sets of images. For example, this one is exactly the same as this one. This implies that these two feature maps will also have one-to-one correspondences. Actually, these two feature maps are related by a permutation, except for some boundary elements. We call these two feature maps as group feature. Then we will get an equivalence that the transformation of the input image results in the permutation of the output group feature. We can see that the permutation preserves the local structure of group feature. For example, the blue square here is exactly the same as the blue square here, but the red square here is the same as the red square here, which includes the rightmost three elements, because the rotation group is cyclic. What we are going to do is applying group convolution to exploit this local structure. The group convolution here is very similar to conventional convolution, except that it respects the structure of the underlying group. For example, to get the feature vector on this blue grid, we need to pad the feature map circularly. Meanwhile, we can see that the group convolution preserves the equivalence property so that we can stack multiple group convolutions to form a group CNN. Finally, we use bilinear pooling to extract a single invariant feature vector from the equivalent feature maps. And actually, any pooling like max or average pooling can do this work, but we adopt bilinear pooling because it's more expressive. In summary, the whole architecture is shown in this figure. Given an input image, we first warped it with a predefined set of transformations. Then, on each warped image, we apply the same vanilla CNN to get a set of feature maps. Then, we interpolate feature vectors of a specific point on these feature maps to get a group feature. Finally, two group CNNs and a bilinear pooling are applied to get the final gift descriptor on this point. As shown in the left figure, gift can be used for dense correspondence estimation since it does not rely on the detected scales and orientations. In the right figure, we systematically increase the rotation and scaling to test the robustness of gift. It shows that the performance of gift drops slowly. Our second part is the correspondence filter GMCNet. Matches produced by nearest neighbor searching inevitably contain lots of outliers as shown in right figures. Meanwhile, robust estimators like RANSAC can find inliers by fitting a geometric model, but are often vulnerable to outliers. It's a natural question about how to detect outliers by other clues. If we separate true correspondences from false correspondences, we can see that true correspondences are usually motion-coherent. It means that they have consistent direction and motion, while false correspondences just scatter randomly. The motion coherence of correspondences originates from depth. A scene usually consists of a piecewise smooth depth field. Here we show 4 regions which all have approximate smooth depths inside. The motion of camera will cause a smooth motion in each region, so it will result in a piecewise smooth motion field. Such motion fields can be used to explain these true correspondences. The key to find motion-coherent correspondences is to find the motion field. However, finding the piecewise smooth motion field is quite challenging here. First, the correspondences are very sparse. In our cases, we only have about 2,000 correspondences for an image pair. Second, the criteria of smoothness are ambiguous and need to be carefully selected for different datasets. Third, the putative correspondences usually have very high outlier ratio. To address these problems, we design a network called Graph Motion Coherence Network to learn motion coherence from sparse correspondences. The proposed network only takes coordinates of correspondences as input so that it can work with any feature detector and descriptor. In the network, we use two graph-based local operators to help the network find motion coherence. We designed these operators based on two observations. The first observation is that motion-coherent correspondences have supporting correspondences in their neighborhood. Such supporting correspondences have consistent directions and motions. In contrast, for the false correspondences, their neighbors scatter randomly. In light of this, we propose a local graph convolution to check whether there exist supporting correspondences in the neighborhood. The local graph convolution takes differences of both features and coordinates, process them by a multi-layer perception, and max pooling to get the output feature. Our second observation is that consistent correspondences should have similar features to each other. For example, if we find the green correspondence in the top cluster tends to be a true correspondence, then the rest yellow correspondences in the neighborhood also tend to be true correspondences because they are consistent with the green one. Motivated by this, we propose an isotropic graph diffusion to propagate feature among correspondences. We use a multi-layer perception to predict the connectivity between correspondences according to their motion and the feature consistency. Then, we normalize the connectivity and propagate the features according to the normalized connectivity. Such graph diffusion can help the network to find more inliers so that it can help the network improve the recall of true correspondences. Here is the architecture of GMCnet. GMCnet takes raw correspondences as input and outputs their probability of being inliers. We first construct a graph on the correspondences by connecting every correspondence with its k-nearest neighbors according to their coordinate differences. Only few edges are drawn in the figure for simplicity. Then, the local graph convolution is applied to compare motion differences between correspondences. It provides helpful information about supporting matches for localizing motion-coherent correspondences. In the following, we adopt a global clustering layer implemented by diffpool and diffarmpool. The global clustering is used to find global motion coherence and the underlying epipolar geometry among correspondences. However, such global clustering may neglect the local feature similarities between consistent correspondences. To amend this, an isotropic graph diffusion is applied to propagate features according to their motion consistency, so their feature similarity are enhanced and will help the network to find more inliers. Moreover, the learned motion coherence is also applicable to image pairs of dynamic scenes. Here we show some results on the Davis video dataset. The top line is the input correspondences and the bottom line is the output correspondences of GMCnet. We only draw correspondences on the foreground object for better visualization, and in fact, the input to the GMCnet is all correspondences, including the foreground and the background. In the final part, we introduce some implementation details about our submissions. For the detector, we use the official pre-trained model directly, and we only use the detected location of KeyNet. For the gift descriptor, we only consider scale group in our submission, we sample 10 elements on the scale group with an interval of square root 2. The vanilla CNN has 4 convolution layers, and each group CNN only has 6 convolution layers. To train the gift descriptor, we use a triplet loss with a margin of 0.5, and the model is pre-trained on a synthetic homography dataset and fine-tuned on the provided IMW training set. As for the GMCnet filter, we use the mutual nearest mask and descriptor distance ratio as the feature of correspondences. And our model consists of 4 graph convolution layers, 2 global clustering layers, and 4 graph diffusion layers. We use the geometric loss and classification loss to train our model. The model is trained from scratch on the provided IMW training set. We use the provided DGensec with a max iteration number of 100,000. The inlet thresholds are selected based on the performances on the validation set. In conclusion, gift descriptor is designed to be invariant to scaling and rotation, and GMCnet learns motion coherence for correspondence proving. Our models achieve competitive performances and are trained on the provided training set only. Thank you for your attention.
Okay. Again, this was a video. I don't think we have any of the authors on chat. If we do, please let us know. But otherwise, we'll move on to the next talk, which should be by Andrea. Luca Cavalli. Luca?
Yeah, hello, can you hear me?
Yeah, that's fine. Can you share your screen?
Yes, sure. Okay. Okay, can you see my screen?
Yep, that works.
Okay, good, thank you. So we are going to speak about our submission, of course, and mainly about ADLM, which is the core of this submission. So first, an overview of our submission. It's quite standard for most of it. So we first extract 8,000 DOG key points, the provided script from the challenge baselines repository, and extract upright patches and extract HardNet descriptors with, again, the pre-trained model from the same repository. And out of these key points, we perform matching and outlier filtering with ADLM that we're going to explain in the following. And finally, we just ran 100,000 iterations of DGensec. So then what is ADLM? ADLM stands for Adaptive Locally Affine Matching. It is a simple and fast handcrafted method for outlier detection, which does not involve any learning, which is quite particular within this challenge and this recent methods. So at the core, inliers are detected by checking for local affine agreement. But why adaptive? Well, in the figure, we show correct correspondences in green, and red lines are the, on the right image, are the errors with respect to the least squares affine model fit on correct correspondences. As you can see, errors can become quite large, even for correct correspondences, due to non-planarity and perspective deformations. So in challenging image couples, affine models are not really exactly expressing the image motion. So as a result, we do not define a fixed threshold on affine errors, but rather we search for statistical significance in error patterns. So this is the adaptive nature of ADLM, so that we define an adaptive thresholding scheme. Overall, this is the pipeline ADLM follows. So we first extract nearest neighbor correspondences, which are quite chaotic, of course, and then select a small subset of those to be region correspondences, which are just a rough indication of region correspondences that do not really need to be correct. They are an indication for a further search afterwards. Then for each region correspondence, we run adaptive local affine verification. And this actually filters the nearest neighbor correspondences locally. And finally, we sum up, we merge all of these filtered correspondences to get the final output. So we will detail a bit more on the important steps. So region correspondences are selected to cover the full area of the first image, while maximizing the reliability of the correspondences. In particular, this is implemented as a local non-minimum suppression over the ratio test score applied on the nearest neighbor correspondences, so that given selected region correspondence, we guarantee that according to the ratio test score, this is locally the most reliable correspondence that we can draw. And overall, we cover the full image. Then each region correspondence undergoes the process of affine verification. This is implemented as a GPU parallelized RANSEX fitting centered affine transformations. We observed that 128 RANSEC iterations with PROSEC-like sampling are enough, and we use this hyperparameter for this challenge, as we only need to draw 2 samples to fit a centered affinity. So this step is quite efficient. As we mentioned, however, our RANSECs do not label inliers by means of a fixed threshold. Instead, we label inliers based on this confidence measure that we propose. So our confidence measures the discrepancy between the observed affine error patterns, PK, and the patterns that we would expect to observe under the hypothesis of having just uniformly scattered correspondences. So that patterns that are very unlikely to be observed at random then cause a spike in this confidence measure, and they get detected easily. To give an idea of how this confidence measure works, for uniformly scattered correspondences, you would expect this confidence to go to 1, of course. And for the threshold in the challenge, we used a threshold of 200. Moreover, EDELAM overall is designed to be massively parallel, and so it's quite fast. So running matching and filtering of image pairs with 8,000 key points per image, we could go to 50 frames per second on a modern GPU. And in the plots, you see how these changes with changing number of key points per image with speed in FPS, and also GPU memory usage, which is quite important if we want to use GPUs for this. And finally, we want to underline that this is only it's just an applier rejection step. This means that it can be basically included quite easily in most sparse vision pipelines. So that's indeed exactly what we did with our submission to the challenge. So we took the best baseline from the challenge authors, at least for the baselines of the challenge, the initial ones, and indeed this was the HardNet upright descriptors with DigInsect filtering and ratio test. And instead of ratio test, we apply EDELAM, and we observe the improvement, the difference. So what we observed indeed was quite a big step upwards in the multi-view task especially, and a smaller step upwards on the stereo task as well. We believe that the reason why the multi-view task gets the best advantage from Edelman is because with the redundancy of views and observations, the CallMap with multi-view is able to average over more noisy inliers that Edelman does not discard. Indeed, Edelman keeps quite a lot of inliers, even though sometimes they're a bit noisy. And this is more of an advantage for multi-view rather than for stereo, which gets still an advantage, but smaller. So overall, as a summary, we saw that Edelman is a simple method, which is at the same time quite fast and effective. And so it is an outlier filter, which is quite easy to tune and can be used as a plug-and-play module inside sparse vision pipelines. And still, it's very competitive with recent methods. You can find it on arXiv, and to know more about more details about the method. And you will soon find code in GitHub, which we will release. And so thank you. And if you want, I'm available here for any question. Otherwise, you can write me an email.
Okay, thank you so much. Yeah, that was fantastic, especially given that with the abundance of learned methods, it's really refreshing when we see these more traditional type methods that actually are. I really love it.
Yeah,
so
thank you.
A quick couple of questions that we have is how important is the verification step? For example, you use regions and then you verify it. What happens if you don't verify it? Because it seems like the non-maximum suppression with the ratio test might actually be good.
So exactly what do you mean if we don't verify? Like you mean we just skip the step of spine verification? And well, that in terms of the HLM pipeline, this would mean just output nearest neighbors, right?
Well, so basically using the region correspondences as if they are actual.
Oh, you mean, okay, you mean just using region correspondences.
Exactly.
Well, they would be quite sparse. And as you see from the figure, this is an actual output from the step in Edelman. You see, you would lose a lot of information because it's just a few which are correct and a lot of them are quite wrong. Because the main requirement here at this step is just coverage. And then the final, the subsequent step will give, will take back all of the lost information. So just region correspondences would be probably quite bad.
I see.
At least for how it's set up like this.
I see. Very cool. And how important is the adaptive Ransec threshold? How big of an effect does it have on?
Okay, I see. So yeah, we did some experiments and ablation studies. You can find them in the paper. Yes, indeed, it improves over just having a fixed threshold. Indeed, it takes out the burden of choosing the right threshold because it's quite easier to choose the right threshold for this confidence measure. But if we ran some extensive search over several thresholds to find the best one, and we found out that indeed localization performance is not extremely different. Still, it's different. It's like a bit higher if you go on the confidence, and if you also look at inlier F score, also it's quite higher. Like we observed that you can't really get a single threshold to be very effective in selective many correct correspondences and having very, very good estimation at the same time, while you would get both kind of together with this confidence measure without too much tuning indeed. So it's quite an advantage in that sense.
So finally, we have a question in chat from Tantaki asking about whether the method can be easily adapted to multi-grid objects, multiple rigid objects.
Multiple rigid objects, you mean?
Yeah, so not only a scene, but let's say you have multiple objects moving in the scene. Would this method be tracking?
Well, yes, indeed, this method, I would say, just generalizes out of the box to this problem because it's only local. It's not checking for any global transformation. So we don't have any assumption that that we are observing just a scene which is rigid and we are moving from one view to the other. So we don't assume there is a fundamental metric mapping from one to the other. We just assume there is a local fine transformation here and there, and they don't need to interact between those. So if you just have multiple objects moving around, you can still use it just as it is.
Okay, thanks for the presentation. Really nice work. I really have to read the paper. Can you stop sharing your screen so we can move, thank you, to the next speaker, which is Michal Tyszkiewicz. Michal, you around? And here we go. Can you say something?
Yeah, I have to unmute myself. Okay, can you hear me?
I think your volume is very, very low.
Okay, then 1 second. I need
to. You try speaking closer to the microphone or
increase the volume.
Seems better now.
How about now?
Oh, now it sounds quite good. Yeah.
Okay, great.
Yeah, go on.
Can you see that presentation?
Yeah, that's fine.
Great. Okay, I'll be talking about my entry, which is DISC. It's about learning local features with reinforcement learning. So after this brief refresher with no learning in the previous presentation, now it's all about all-out machine learning with end-to-end pipeline. So what is the problem with most end-to-end detection and matching pipelines is that good features can be defined as any features which can be reliably localized and matched with descriptors. And at the same time, good descriptors are any descriptors which reliably match features. And then there's a chicken and egg problem, which is where do we start? And most end-to-end pipelines like to start with reliably localized, that is repeatable features, but that's not necessarily the right way, as I will show later. And the insight in this work is if we focus on matches instead, those two problems basically disappear and magically get merged into a single optimization problem. So what are the postulates for our method? Where we want to find features and describe them jointly with a single CNN. We want to find descriptors for the features which are yielded by our detector. In particular, we do not care about what the descriptor would be for any other location that is not being picked by the detector. We want to detect features which will perform well in matching. And what this means in particular is a repeatable feature, maybe very repeatable feature. It is still a poor feature if it is being mismatched, or for instance, if it reappears with almost no changes many times in the scene because it's just some geometric pattern that keeps reappearing. And on the other hand, a random point in the sky that you would say is a terrible feature, it's not well localized, it's not really a problem as long as it's not being matched and not causing errors for the geometry estimation. So the namesake for DISC is discrete keypoints because it leverages principles from reinforcement learning to actually sample the keypoints during training and then actually perform the matching and evaluate how good the matches are to approach the actual inference regime much closer than most other methods. So how does it work? We first define a probability distribution over features, given the image and some weights of the feature extraction and detection network. Those are called θF. We relax matching from deterministic nearest neighbor with ratio test or something to a probability distribution over matches, given the features detected in 2 images and some parameters. This could be a neural network, but in our case, it's a very simple relaxation of cycle consistent matching. So it's just a single parameter there. Then we define a reward for any potential match between some feature I in image A and some feature B in image J, some feature J in image B. And then we maximize the expected reward. So more concretely, we use a UNet to densely compute descriptors and the feature heat map. We then subdivide this heat map into 8 by 8 cells and sample at most 1 feature in each cell. Then we associate them with the descriptor at this location that was already pre-predicted by the UNet. Then, as I said, for the matching distribution, we have a relaxation of cycle consistent matching. So we just, according to the distance matrix, we sample some choice for each feature in image A, and then some choice for each feature in image B, and we declare an actual match whenever the 2 agree. And for the reward, we say that we will give the algorithm 1 point whenever the match is correct, and we'll take a quarter away if it's incorrect. And for whether it is correct or not correct, we use depth and ground truth camera pose to find whether the 2 actually correspond. We also have a variant which uses no depth maps and only ground truth pose. And then once we have this in place, a seminal work by Williams gives a formula for an estimator of gradient of the expected reward with respect to any parameters involved. This is called the reinforce algorithm, and you may have heard of it. And once we have that, we just train with gradient ascent to maximize this expected reward. So how does it look like? This is an image with all the features detected, marked with red dots. Here is a close-up. When my supervisor first saw that, he said, wait, those don't really look like features. What are they supposed to represent? And this is an intuitive insight. Nevertheless, they work quite well. And if we look at stereo results with 2K features, when comparing with the upper row, which is baseline DOG features with HardNet descriptors, and we compare with the lower line of disk, we see that our matches are quite consistently much more dense. And if they deal with quite big changes in scale, and they do not deal well with rotations. And at this point, I should stress that our method uses no data augmentation whatsoever. So this is largely possible to deal with by data augmentation, which we didn't really employ. When we go to more features, the qualitative result remains the same. We have more dense feature matches. But I think the really interesting part happens when we look at multi-view results, where we have that our features cover the images much more densely and almost uniformly, which is not the case with, for instance, DOG features that you see at the top. And especially if we go to the 2K features regime, you see that DOG features are all concentrated in this text, head and hands, or maybe on the windows and turrets. And any method that wants to leverage SIFT features is basically capped at the performance of matching the features that it's given, whereas our method yields much more evenly distributed features, which in the end gives us better estimation of the 3D geometry when, for instance, reconstructing point clouds. So if we go to other scenes, we keep seeing the same picture. In particular, this Piazza San Marco scene is only basically reconstructed in this very tiny region by DOG, whereas our algorithm finds a much broader, so to say, support for the finding the features. Now, if we go to a bigger reconstruction, this is with 1,200 images. That's the validation set for this benchmark. We get a bigger model than SIFT baseline in this case, with much more observations per landmark. And even though you can say that SIFT descriptors managed to correctly match basically every detection that they made that is feasible to match that lies on the building, it is not very dense and it is not very equally distributed, resulting in quite spotty coverage of the 3D model with matches. Whereas in our case, we have basically dense coverage of the whole structure with our features, and therefore we have a very nice matching picture on the point cloud, which looks almost like the actual field of view from this perspective of this image. And now my point to make about repeatability and what is really important, whether we should consider only repeatable features and then build descriptors on top. This is a scene from one of the benchmarks from ETH, and it's really peculiar in that if you look closely at this patch that is specifically designed to be matched by computer vision algorithms, you will see that our method picked a point everywhere except there. And at first it may look like a very odd decision because this is an incredibly salient point that is very reliable. But on the second thought, you will realize that this area is otherwise completely textureless, and it could be very easily that there are many such patches in this image, and then they become easy to confuse. In fact, there are 2 more such patches, and it's not so easy to distinguish them. Whereas our method decides to instead sample key points which lie in not so salient regions, but ones that are rich in high frequency features, which are very unlikely to repeat across the image, therefore make for easy matching. And to address some discussion that we had in chat, there is also a comparison of our model in the upper part trained with depth-based supervision, which basically learns to guess where depth maps are available and therefore only samples point within the image and not at the edges, because this is where the depth maps are flaky, compared with a model which is trained with epipolar constraints, which is therefore not constrained to the regions with provided depth maps. And it has this strange byproduct that on one hand, it avoids this bias. On the other hand, it samples feature points that lie outside the building itself, because it finds out that those points are still matchable based on the context visible nearby. So what do the numbers look like? Okay, there's another example of this phenomenon on the St. Peter's Square. What are the numbers like? So if we look at the 8K feature bracket and we compare with the winning entry and the best entry that used built-in matcher, like our method does, we will see that we are off in terms of mean average accuracy. But at the same time, we have number one repeatability, even though we do not explicitly optimize for repeatability at any point. And we have twice the number of Ranzak inliers. We have second of all methods number of landmarks in 3D reconstruction and significantly more than the winning entries. We have much bigger track length. And in general, this means that even though the camera pose estimation suffers compared to the winning entries, we still have really good models that come out of this. And perhaps this is a good building block for future work. Now, if we look at 2K bracket, it's a bit easier because disk is actually the best entry that doesn't use custom matchers. The image is quite similar. We have quite a lot inliers, even though SuperPoint with SuperGlue finds a bit more of them. We are still very repeatable. We have high matching score. We have lots of landmarks, very high track length. And overall, it still points to this phenomenon that surprisingly scoring very well in those side categories doesn't necessarily translate to camera pose estimation accuracy directly. So what are the takeaway messages? First, that there is more to end-to-end pipelines than a single network, and loss unified as alpha times 1 loss plus beta second loss. You really want to have the loss care about the downstream task and not merely optimize all parts in separation, like all tasks in separation. Secondly, that reinforcement learning gives a principled approach to learning sequential discrete decision-making, and first picking discrete key points and then matching them is an instance of this problem. Then that I have a method which gives very novel kind of features which are repeatable, which are dense, and which are reliably matched, as weird as they may look to someone familiar with local features. And that the above is insufficient to yield state-of-the-art camera pose estimation. I think that the main takeaway of this benchmark is really that intelligent, clever way of doing the matching that uses global context rather than just descriptor distances is the key. And here is another point with the method, that our approach is completely orthogonal to those intelligent feature matchers. And in fact, it seems quite plausible that disk with SuperGlue would outperform disk with SuperPoint just because disk is more repeatable and denser and seems to give better matching than SuperPoint does. And one does not see a particular reason why SuperGlue should perform particularly well with SuperPoint specifically. Then our approach is also orthogonal to the source of the training signal. We only really supervise the matches that it proposes to us, and rigid geometry is just one option. Another would be to look at multiple moving objects and somehow align them. Another would be to have people walking across different video frames, and if you have a way to tell that a match between the same person in different frames is good, then this method is ready to learn how the clothes change their appearance as the person walks, how the very non-rigid physics of body work. And all of this can be very easily integrated in this pipeline as soon as you have the reward signal. So with this, I would like to thank you for your attention, and please stay tuned for the new RIPS release because this work is really a preview for that.
Thank you for the presentation. We have one question, which is there a preprint for this? The answer is not yet. It will be on archive soon, but we have to jump through a couple hooks because I'm in it, unfortunately.
I have a question, actually. So why did you choose policy gradient justice? Because it works, like as far as I know, PPO is kind of state-of-the-art of RL methods.
Sorry, I didn't get your point. You said whether I use policy gradient as opposed to Q-learning, or?
No. Why did you use policy gradient as algorithm, and which flavor of it did you use? So have you explored the different RL algorithms?
No, I haven't done much exploration. I used policy gradient, the simplest variant, because it's easy and quick, and also because I think that this work is a very particular regime, so to speak, in that when you think of problems like playing Go, the problem is really about very long horizon of making one decision after another, and you don't, like, if you win in the end, you have no clue whether this victory was due to this decision made at turn 15 or 30, whereas in this case, there's basically 2 steps at which I make decision. First, I make decision about all feature detections all in parallel at 1 step, and then I make another decision about all matches all in 1 step. So there is very little of this temporal problem. And also because I have per match supervision, I can tell for every particular match that it was correct or it was incorrect. And I don't have to disambiguate their mutual influence on each other. Yes, so this is why I use this simple algorithm and why it works. I made an attempt to use the very simplest improvement to reinforce, which is adding baselinings. That's a way where we subtract the expected reward. It's normally improves convergence, but in fact, I didn't see any improvement. This method already converges very reliably. So I think it's a very particular edge case where I'm between computer vision and reinforcement learning, but really, really close to computer vision.
I see.
Wow,
So
cool.
you're saying that because there's no large temporal trajectory that you need to estimate, there's no, not much variance reduction that you need to do in terms of RL literature, I guess.
Yes, so there's a bit earlier paper than mine, which tries to do something that superficially looks very similar, it's called reinforced superpoints, and they use a similar framework and they optimize for camera pose directly. They run Ransack and they get feedback the camera pose. And I believe they deal with much more of this problem because they don't have a per match feedback. They only they make decision about, say, 8,000 features, then about 3,000 matches. And at the end, they get one number that's supposed to supervise this whole lot of decisions, in which case it's really difficult to tell which ones were the correct ones and which ones just happened to jump on the bandwagon. But in my case, I have per decision, almost per decision supervision, and this makes it much easier.
I see. Although you're using policy gradient, this is more like supervised learning.
Yes, it's almost there.
Yeah.
Should I stop sharing? What I do?
Yes, please.
Yes, please.
No, it allows me to do stop share here. Okay, thank you.
So I guess I can move on to our final challenge talk. It's a video talk again from Ping-An. And without further ado, I'll just let the authors speak for themselves in the video.
Title is Pipeline, Keypoint Select, and HardNet Circuit 4, and SuperGlue. First of all, let me introduce my team member. 许明正、盛和、杨柳、关林梁、文边李、优吴、宪忠。If you have any question about my method, please let me know. You can contact me by the email you list on the leaderboard page. This is a catalog of my short talk. I will talk about my challenge pipeline and then analysis and to-do. As shown, the pipeline consists of Keypoint Select, HardNet Circuit 4, SuperGlue. First, I'll talk about the pipeline module Keypoint select. This is how to construct the dataset for Keypoint select. The right picture shown. Label positive. Pixel color is not red, and also it's surround arrow 8x8. The rest pixels are all negative. Patch the extracting. Merge point XS from images point by with shift points to get the keypoint score entry. Extract patches like benchmark, and patch shape is 64x64. Keypoint select network. HardNet backbone. R2net. Also, I do some changes. Extend the input layer from 32x32 to 64x64. And then double every combinational layer channels. At last, add softmax to classify the input, positive or negative. Maybe the picture below confuses you. Sorry for that. I have no time to draw a new one. This is how to train the Keypoint select model. No more than 500 images per scene. No more than 500 positive XS per image. Balance the positive and negative samples. Epochs is 10. Batch size is 256. Learning rate is 0.01. And we adopt a DAM optimizer. At last, we got 81% accuracy. We got the best result at epoch 8 and got no improvement, even with more samples, also steps. This is how about the performance about Keypoint select on the challenge tasks. On 2 key descriptor tasks, we got more than 5% absolutely improvement on VR scenes. On 8 key descriptor tasks, we got no improvement. Otherwise, go down a little bit. And I'll talk about HardNet 64. This is how to construct the dataset for HardNet 64. Get the Keypoint score and angel. We run the Keypoint XS, get from images point bin, and then merge them with shift keypoints. IOU filtering. Construct the rectangles centered on every keypoint per image and sort them by keypoint score in descending order. And the rectangle shape is 64x64. Then delete rectangles with a ratio of intersection error greater than 0.6 and a lower score. Construct the patch pairs. Get the Keypoint collection. All other XOS related with the same 3-dimensional points in each scene. Got the Keypoint pair, or the binary combination of Keypoint collection. Extract the patches. Get the patches from gray image, almost like a benchmark based on Keypoint info. And the patch shape is 64x64. This is the HardNet 64 network. HardNet backbone. R2net also do some changes. extend the input layer to 64x84, double every convolutional layer channel. This is how to train the HardNet 64 model. Extract samples. Randomly extract 500 patch pair per scene every epoch. 1 patch pair per 3D point. 14 scenes total. Anti-Peter squares added. Hyperparameters. Train the model with the epochs is 20. 700 steps per epoch. Batch size is 1024. 140,000 matching pairs at the very most, and learning rate is 10. HardNet 64 model training. Loss and optimizer. We use a quadratic Hangzhou triplet loss inspired by ASLFeat. We use a DMW optimizer with learning rate is 10 and other default settings. We adopt warm-up linear schedule method regarding learning rate schedule, and warm-up steps is 0.1 x 140,000. Fine-tuning. We also fine-tune the model with epochs 2. Learning rate is 0.1 and other parameters unchanged. Result, we got RPR is 0.002. This is the HardNet performance on the challenge tasks. On 2K descriptor task, we got a MAA is 0.4098 up to 10 degrees averaged over stereo and multiple tasks. On 8K descriptor, got MAA is 0.66999 up to 10 degrees averaged over all stereo and multiple tasks. And then I'll talk about SuperGlue. This is how to construct the dataset for SuperGlue. Get Keypoint info, merge Keypoint XOS, get from image point bin with shift Keypoint by KNN. Use the L2 distance to get the Keypoint scale, score, and angle. Data filtering. Delete images on which the number of merged Keypoints is less than 2048. Get the image pair. Construct the image pairs 1024 x 1024, 1024 x 2048, 2048 x 1024, 2048 x 2048, according to the number of merged Keypoints. Keypoint pair is positive related to the same 3D point, and the rest are all negative. SuperGlue network. We reproduce the SuperGlue method just according to the paper. SuperGlue model training. We adopt the batch size 12, 4, 4, 1 according to the image pairs. 1024 x 1024, 1024 x 2048, 2048 x 1024, 2048 x 2048 because of GPU memory. We train steps 500,000 and learning rate is 0.001, and learning rate decay ratio is 0.00008 with other default setting. This is how the performance on the Chinese tasks. On 2K descriptor, had more than 2.5% absolute improvement on VR scenes. On 8K descriptor tasks, maybe got no improvement. To be honest, we can't improve matches in terms of 8K descriptor because of lack of GPU memory. Instead, we match 7K descriptors by SuperGlue and the last 1K descriptors by Discriminative, but got no any improvement. Now, I'll talk about analysis and to-do. Analysis and to-do. Analysis. Why don't the KP selecting improve the performance on 8K descriptors? Maybe pseudo-ground truth pose and densified depth maps are all got by using default 80,181 and 92 safe keypoints resultantly. Selecting 8K keypoints from keypoints got from lower safe threshold may got noise keypoints, even they are in the target area truly. Why don't SuperGlue improve the performance? 8K descriptor. Because of our GPU memory, we are just able to train the model with no more than 2048 keypoints per image. Thus, the attention layer may not learn more weight parameters than 2048 every 2048. To do greater model capacity. To improve the accuracy of keypoint selecting, we want to try a network with greater model capacity. For example, ASLFeat 151. More scenes. Considering very large relative and absolute errors on some scenes, maybe training a model with more scenes will work. Better matching. Given that SuperGlue don't work on the task of 8K descriptor, we want to explore other matching methods such as PSMNet, StereoNet. Thank you again.
Okay, that was the last of the challenge talks. Thanks for the participants for submitting it. I'll try to share my screen 1 second. We just have a few slides left. That should do it. Okay, so we are almost at the end. I just wanted to add some closing remarks. So to highlight some key points about the 2020 Image Matching Challenge, we received 102 submissions, which is pretty nice, up from about 28 last year, plus the many baselines that we computed for the paper that nobody had to run. We had submissions from about 23 different teams, from 13 in 2019, so also an improvement. I'm very happy to see different types of contributions. So we have, for instance, incremental improvements such as patch descriptors that you retain on a different data set, just trying to do the kind of things that you would expect people have to do well in a challenge, but also from new handcrafted methods such as ADALAM that Luca showed us, to radical departures such as SuperGlue using graph neural networks or DISC using principles from reinforcement learning. This is still nothing that's fully end-to-end yet, but I think we are getting closer. So let's see what next year brings up. It's interesting to see that most top submissions used custom matchers, not all of them, but most of them. This is a big departure from last year. It was organized a bit last minute. So we always expect that people would submit custom matches and not only just give us the features. And that is why if you look at the results from last year, the multi-view task is kind of comparable, but stereo went up a lot. And that is the reason why. So to recap, we started working on this, what became the benchmark and the challenge more than a year ago. The idea was to provide people, researchers like us, a full pipeline that can be used to evaluate performance of the things that they are working on, the new methods that they are developing on downstream tasks. So things like stereo or SFM, structure from motion. This requires a modular framework, because as we see, you have to do all these different steps. You have to extract the features, you have to match them, you have to throw them into a stereo algorithm, such as runstack or digenstack, or into structure from motion for the other task. And this is actually a lot of work, not only in implementing these things, but in putting them together and figuring out how to tune them. And there is no need for everyone to reinvent the wheel every time. So hopefully this can make people's lives easier. Is it actually working? So I see that we are getting some visibility in the sense that several papers are already using it to let's say, evaluate their method. So in my paper, I want to say, look, I submitted the results for my algorithm to this benchmark, and I got these numbers, and they are pretty good. So it shows that this is working, and it's working against finely tuned baselines, and competing against the real state of the art. And it seems that we are getting some traction in that sense, which is very nice. And I think it's a bit unwieldy for a benchmark, because as you have seen, it's not something that is easy to let's say, score like you would have in an image classification challenge, right? You still have to run this benchmark. You still have to do stereo, etc., to have to do structure for motion. But it's becoming easier to use, and several challenge submissions, I think, if not most of the top performing ones, have already been tuning on our validation set using the benchmark. So that is pretty nice. For next year, I want to say that we will try to hold, I expect that we will hold the 2021 image matching challenge. So please stay tuned, please submit again if you are working on these topics still. The code base is pretty stable at this point, so you can just use it. You can download it from GitHub. You can, if you see problems, you can let us know. You can submit improvements directly. We do not want this to be only like a challenge that works for a few months a year. So evaluations will be conducted throughout the year. You can submit new entries now. We'll have to find a way to tag these. So like this is 2020, this is 2021. If something changes, we might need some intermediate tags. But we hope that people use it for the new RIPS deadline, for the CVPR deadline, and so on and so forth. So that is one thing that we have improved a little bit lately. You can use it in your papers, and you can make anonymous submissions. Not anonymous submissions like they were in the sense for the challenge, where we have unmasked all of the anonymous submissions that we had for the challenge. But you can also add a new flag on the metadata fields, just mark under review as true, and we'll keep it anonymized for up to a year. So we know that everyone just submits everything on archive as soon as they have a paper nowadays, but it's still good to keep up the appearances and allow people to make anonymous submissions and link them to, let's say, my CVPR submission 1248. So you can do that now. We are still working on new features. There is some low-hanging fruit. We have talked about post-based submissions for quite some time. I think that would allow us to receive solutions that come from, like, let's say, dense networks, right? They have two images. I get the post, and I want to see how well that works. So you should be able to do that soon. And also improving the submission process a little bit. So we had 100 submissions, I said, but I think if you count the total number, it was like 130, 140, something like that. And some of them are broken in pretty silly ways, like this doesn't work for some reason and people didn't send an email, so there is no way for us to reach out to them. So that is something that we can definitely improve. There is no notion of teams. There's a few things that we can do to simplify participants' life in that way. On bigger changes, we want to look into bootstrapping the ground truth, which comes from pretty off-the-shelf call map with root Swift features. Now we have some ideas on how to do this better. So hopefully we can come up with a better ground truth, and maybe that helps us a little bit. We also want to try to incorporate more data sets, more tasks, like having indoors data without departing too radically and going into, let's say, Slum. I think would be interesting. We will say more about that when we have it. So please stay tuned, and we'll just post news items on the challenge website or on GitHub. One thing that I find interesting is that we had 3 categories originally, which is the small descriptors, large descriptors, and 128 dimensional descriptors, which is the standard that comes from Swift. In addition to the 2,000 and 8,000 categories, so it was 6 in total with 2 prices. And the 2 prices, we decided, okay, everyone uses 128 dimensional descriptors, so let's try to prioritize that. And that is good, but what it means is that we got basically no traction at all on the other 2 settings. So I think large descriptors are not very interesting because there's only a couple papers that use descriptors larger than 128. But small and binary descriptors are something that is used very commonly in industry. So it might be something that we want to prioritize in future editions. If you have any thoughts on that, we welcome them. And that's about it. Thanks everyone for your attention and for your participation. It's been a complicated CVPR because of the, it's going virtual very last minute and people having to participate from different time zones. But I think it went quite well, and I hope that you enjoyed it. If you have any further questions, please let us know. We can answer them on chat if I don't see anything right now. Otherwise, just shoot us an email anytime.
Self-clap.
That's it.
Thank you.
I think we can call it a day.
Yeah, I think so. Yep.
Okay, thanks so much, everyone.
Thank you.
Yeah, thank you for staying so late for those in Europe. And yeah, I mean, crazy. Why are there time zones? They should get rid of these time zone thing. I keep saying. Yeah. Okay.
Yes, the artist lab.
Yes, yes. And okay, so I'm going to now stop the stream. Fingers crossed that nothing goes wrong, and we could have videos online as well.